All right. Can folks hear us okay? I think they do, so I think we can just get started. All right. Sweet. Fire. Yes. Welcome everyone. I'm actually really thrilled to be doing this. Like we've been on a sort of break since my son came a bit earlier than expected, so it kind of like wrecked the GP mode talk schedule. But like I think we're back in full force right now. So this is a talk that I've been personally like very excited about, just because I'd asked like for some colleagues at NVIDIA, like, hey, like I really need someone to help us understand like what the heck is going on with like your floats. Do you actually follow the standards or not? How is it different from CPUs? I could hardly find any information. And then when I like kept probing, people told me, hey, you should really talk to Paulius. And like, lo and behold, Paulius is now one of my colleagues in the PyTorch team. So this is how this talk came about. Generally, like what makes this topic interesting is that like silent incorrectness issues are really cursed. Floats are really cursed. This is something like with hardly any docs. And Paulius, well, like Paulius is basically is arguably the man most responsible for sort of the efficiency revolution on GPUs, whether it's like low bit dtypes or sparsity. Most of those papers published by NVIDIA will have Paulius's name on them. So yeah, without further ado, Paulius, please take it from here.
Thanks, Mark. Yeah, thanks for the introduction. And I should mention, yeah, I was involved with a number, of papers and other, I guess, inventions at NVIDIA, but there's, a pretty large team working on all of these things, so I cannot take all the credit. A lot of people did a lot of work to enable all of these things. Okay, so a quick outline, and I think, if you have any questions, either chat, post them in chat or interrupt me. So I don't see the chat since I'm in presentation mode, but I guess Mark can interrupt me and I can try and answer. But don't wait till the end. If something's not clear, feel free to jump in and ask. And a quick outline, just so I guess maybe you have a mental map of what topics are coming in what order. So I'll go through some basics of number representation, and I'll try not to spend too much time there, but I think it will suck up some time. That sort of will lay the groundwork for then talking briefly about the history of different numerics used in AI. And then at the end, I have a few slides on some floating point quirks. I think that's what Mark was referring to by very sort of silent, surprising results. All of those will make more sense once we understand sort of the intricacies of floating point representation. But I figured rather than covering those right after the basics, maybe I'll throw in some AI stuff in between. So there'll be something for everybody, and maybe a ton of folks won't get bored. A quick note, as Mark mentioned, I was at NVIDIA for quite a while, so a lot of the material that I'll be sharing is actually borrowed from my past presentations and papers at NVIDIA. In some cases accredited, and in some cases I just copied the entire slide, so you'll see an outline. Unfortunately, I don't have some of the sort of cool videos of various histograms that I had at NVIDIA, since I no longer have access to those. Okay, so getting to numbers. So I'll talk about real number line, right? There are complex numbers and things like that, but we'll ignore those. So, real numbers are, just numbers that we encounter in real life. And the key to observe there is that there's an infinite number of them, right? So here I just have sort of an arrow sort of illustrating the real number line. And on that, I have a few samples, right? So I have integers like -1, 0, 1, 2. Then I have pi, and pi has basically infinite number of decimal precision digits. So key observations that there's an infinite number of values on the real number line, and both infinite range. So we have arbitrarily small and arbitrarily large magnitudes. And even if we take any two values and make a pair out of them, we'll have an infinite number of other values in between those. So that would be infinite precision. And actually, I forget if I included here a slide discussing precision and accuracy, but yeah, precision is just how many samples you have between any pair of values. So there's an infinite number of those, right? And whenever we talk about algebra, those are the assumptions that you're working with the real number line, which has infinite representation. Unfortunately for computers, they cannot do infinite because memory space is finite, memory bandwidth is finite. There's also a finite silicon area, which means that we can only pack in so much math, either area-wise, which will limit the size of the numbers we work on, or the time that we want to spend on operations is finite. We could actually have arbitrarily large precision representations, but they might require many, many instructions to process. So because of all these limitations for practical purposes, computers go with some finite representations, right? And then by definition, those finite representations of numbers will be just sampling the real number line, and there'll be many, many values that cannot be represented accurately in these formats. So, quick note on terminology for precision and accuracy. Those are often abused, and by me sometimes as well. So precision has a specific meaning. It sort of refers to the sample spacing on the real number line. And we'll have some finer examples later on, but just sort of think of it that finer sampling of the line usually means higher precision, or the other way around. You know, if you have higher precision, you'll be able to sample the number line more finely. A key thing to realize that something can be very precise, but can be inaccurate. Right. And accuracy refers to how close some sample of some format is to the actual value that we're trying to represent. Right. So a quick example of these terms is, let's say, the value pi. If we look at, let's say, 3.141543, it is both more precise and more accurate than just 3.14. Right. So it does have more decimal digits. That's what it gives it more precision. But it is also a better approximation of pi than just 3.14. Right. So this guy has both more precision and more accuracy. Now, the second line is an example of where we are more precise because we do have more decimal digits after the decimal point. So again, we more finely sample the real number line. But in this case, it is a less accurate approximation of pi than just 3.14. Because actually, I think that is correct. Yeah, so it's further away from the real pi value than just 3.14 would be. So that's sort of distinction between precision and accuracy. And in the rest of the slide deck, really, when I'll talk about accuracy, for the most part, it will refer to neural network accuracy, so the quality of the results after the neural network processes the inputs. And precision will usually refer to the mantissa size, we'll get to that, or this sampling of the real number line. All right, so I would say there are two widespread format categories, and we'll just talk about the binary representations, right? There are things like binary coded decimals and so on, but they're out of scope here. And if we talk about binaries, then we'll have some number of bits. So n-bit patterns, which basically means we have 2 to the n encodings of binary strings. And then the question is, how do those strings represent numbers on a real number line, right? And the sort of two categories of representations would be integers and floating point. And there are more things beyond that. I think I'll have one graph without going into details. We can talk through that. But integers, as the name suggests, they represent integer values. And the key there is that they sample the real number line at equal intervals in 1 unit increments. Floating point representations represent both integers and fractions, and they do not uniformly sample the real number line. That's the big difference. What they really end up doing, at least all the IEEE-like formats, they uniformly sample the interval between each pair of adjacent powers of 2. And it's just easier to look at the picture rather than just read text. So the first line is integer sampling of the real number line, right? So as expected, we have integers 0, 1, 2, 3, 4, 5, and same to the negative side. The interval is always 1 unit. And that's what we have in various programming languages when we think about integers. The bottom line is a IEEE-like floating point representation. This one, as we'll see later, is, let's say, with 2-bit mantissas. But you can see that the sampling gets much denser closer to 0. It sort of gets coarser and coarser as we move away. So that's what you would see like on a regular scale. If you put this into the log scale, the picture would look different. But the key observation here is that in this particular illustration, we have 4 samples between successive powers of 2. So for example, if we look at 2 and 4, so that's 2 to the 1 and 2 to the 2, we'll have 4 samples. So we have, let's say, 2 itself, 2.5, 3, 3.5, and then 4 would be the next power of 2. The same is true if we look at the interval between 1 and 2. So that's 2 to the 0, 2 to the 1, again, 4 samples. Same thing is true between 1/2 and 1, 4 different samples. And so that's how you get to sort of a higher density of samples towards 0. And at some point they disappear because we run out of exponent range. So that's a key observation. That's what floating point formats do. So you might have a similar number of samples of the real number line once you get n bits. They're not always quite the same between integers and floating point. We'll see various reasons for that. But very roughly, we can think if we have n bits to represent a number, well, we'll have roughly 2 to the n representations, and it's just a question, how are those distributed on the real number line, and how does that match the applications that we're interested in? Okay, so I'll talk briefly about integers. I have more information in integers, but for the sake of time, I figured we'd kind of transition to floats as quickly as possible. So even when it comes to integers, which at first glance sound very simple, there are different ways to represent them. Right? So there are unsigned integers, there are signed magnitude representations, and 2's complement. So the most popular ones in today's chips are unsigned and the 2's complement. So let's say in C, definitely when you say just int, you'll get a signed integer 2's complement representation on most architectures. And unsigned, most architectures implement them, but there's some overheads, and I'll touch on those briefly. Okay, so if we look at unsigned integers, there'll be n unique samples. Oh, I'm sorry, I'm lying here. There are 2 to the n unique samples given n bits, and they will be 0 and then positive integers in increments of 1. Now, depending on the programming language, there are different mandated behaviors, and in C, integers, and thus also C++, the quote-unquote overflow behavior is to wrap around. So if we think about 8-bit integers, if we have value 255, which is the maximum representable and unsigned 8-bit int, and we add 1 to it, and the result is also 8-bit, well, the result must be 0, right? That's mandated by C. And this actually extra processing that has to happen can result in slower code than if you were using just integers. So this can come up sometimes where you're working on values that would be just unsigned. So for example, in GPU world, that comes up for, let's say, thread block and thread IDs. So those are unsigned integers in CUDA. And
but Paulius, I'm curious about, like, this just seems like a foot gun though, right? Because like you would want the error in this case and tell someone, hey, you got an overflow. How come the behavior was to sort of, like, how could we rationalize this sort of behavior in the design of the
that I don't know. I don't know the history behind C requiring that. But from my limited understanding, what happens to sort of guarantee this behavior, extra processing has to happen. And then at least in CUDA land, the way that manifests is that oftentimes you end up using more registers per thread compared to what you would get if you just switch to unsigned integers. And I give an example here where we were working on a layer norm kernel. The kernel was handling 128 elements per thread. So the register use per thread would be quite high, at least 128 plus auxiliary registers for indexing things. And all the indexing was sort of thread ID and block ID based. And if I used unsigned integers for, let's say, indices to access memory, then I was using 168 registers. If I used signed integers, I required only 143 registers. And when the delta is that large, things can actually affect occupancy and your performance. Now, some of that might be compiler not being as stingy with registers as it could be. But my understanding is that it's that unsigned integers in C and C++ come with some extra requirements that compilers sometimes will end up using more registers for, or extra instructions. But in general, maybe Mark, to your question, so integers don't really have, I guess, any kind of sort of overflow behavior like floating point do. So there's the notion of overflow is not really native to integers at all. So for signed integers, there's no definition what happens when you, let's say, increment the largest positive integer. Usually, I think in implementations, it just turns into a negative value, which is arguably even stranger. But
yeah, I mean, I understand, but like, so then like different hardware vendors will take different like choices and they'll be unpredictable. It's just that, like, again, when I'm adding numbers, I don't expect to be doing like a modulo operation over like the max representable value, really. But
right.
Yeah, sure. This is the behavior, so be it. Yes.
Yeah, but that's one thing to keep in mind if you're working with integers, which can happen, and they can actually get used in AI for values as well in some cases. Keeping in mind whether to use signed or unsigned, you kind of have to think about, okay, do I need like an extra power of 2 range for the integers, or do I not need the full range and I can sacrifice 1 power of 2 because I will not hit these quote unquote overflow behavior, and then get more speed, or at least sort of low resource usage, and then go with signed. So something to keep in mind. This is not super widely known. I think NVIDIA's optimization slides from this year's GTC mentioned that in one slide, but it's, yeah, there's not a ton of material on this. And if you look at Stack Overflow, there's debates about that, and people implement various micro benchmarks, but it will be compiler and I think hardware specific.
So Vipul is asking a follow-up question here, which is, so wrapping around happens for signed integers as well, but just at the software level, not really within the hardware.
Okay, yeah. I mean, in software, you can technically implement anything. And I think something will happen at the hardware level as well. And that's probably, again, specific to a particular chip. If we take signed integer, I guess the maximum magnitude would be for 8 bits, 127, I think. So if you add 1 to that, you can check on your platform what happens in pure hardware. Okay, the next representation is signed magnitude. There's not much of that in hardware that I'm aware of, but the reason I mention that is because once we get to floating point, there's sign magnitude aspect there. But the idea is that you have 1 bit for sign, and then remaining n-1 bits go to represent the magnitude. So one property of this is that you get symmetric sampling around 0, right? So you have same number of positive and negative values. It does imply 2 representations for 0. So you'll have both a positive and a negative 0. So this can be viewed as wasting 1 sample on a real number line because they really correspond to the same actual value. But it can also be used for sort of like Lamport style signaling, right? So this can come up, and I think this can be seen in some of NVIDIA's code for communication, where you're trying to minimize synchronization cost. So usually that's for latency limited cases. I think you can find that in some nickel code nowadays. The idea is that the receiver needs to know when the bytes that it's reading have been written by the source of the information, and that can be done through signaling through separate flags, and then you need memory barriers, and that will come with some overhead. But another approach, sort of like Lamport style approach, is you can initialize your data to some invalid value that that your application will not generate, and then the sender can just override it, and the receiver can just busy spin on that region, waiting for the values to change from invalid to something that's valid. And then as soon as it sees the value change, it can actually process it. So there's no need for barriers and synchronizations. So this is where, if you guarantee that your application, for example, will not generate negative zeros, you can use that negative zeros, that special value, right? And that comes up in floating point as well. So that's one aspect. You kind of lose a sample, but you could repurpose it for something else. And it does come up in some AI-related use cases where you're trying to push the performance to the limit. And finally, 2's complement. So this does represent signed integers. It's the most popular sort of implementation in hardware. It does have only a single 0 representation, and but it is asymmetric around 0. It will have 1 more negative sample than positive, right? So for 8-bit integers, you'll go from negative 128 all the way to positive 127. That usually doesn't matter. There's been some studies that suggest for AI, generally you want your sampling to be sort of centered at 0, especially for training. And that's probably more true for lower bit representations. So you don't sort of like biasing during quantization. So oftentimes what happens when people use integers for AI is that they ignore, let's say, negative 128 for 8-bit. So they only use negative 127 to positive 127 range. And that's where various quirks come up, because let's say you have to really match up what your quantization sort of library or software does to what the software that's executing the neural networks does, because they might have different assumptions. But that's 2's complement. Okay, so moving on, really briefly on integer adoption for AI. So they've been adopted mostly for inference. There's some use of integers for training. So there's a blog post by TPU folks from a couple of years ago where they used AQT to train with integer representations. Other than that, I think training is mostly floating point, and inference started using integers fairly on. If I think about, 10 plus years ago, there was integer use for inference. And so the pros of integers for AI is that in the early days, it was really the only way to go below 32 and later 16 bits for your math or representation in memory. That was still supported by hardware you could get. Right, so hardware was mostly FP32, I mean, FP64 as well. Not a lot of people used FP64 for neural networks. So it was mostly single precision floats for a long time. And then FP16 started emerging. Later, BF16 came up. But if you wanted to go below those data types, integer was basically the only way to go. You would save memory footprint as well as memory bandwidth. You could also get higher math rate on both CPUs and GPUs. Right? So for example, if you wanted 8-bit representation, you had to go with integers a while ago. The cons of that, yeah, go ahead.
So over the years, like, I mean, I've seen like a few people sort of post proof of concepts of like integer training, like working well at like smaller scale. I think no one figured out like a good recipe to make the training stable for larger models. But do you think there's like sort of more fundamental reasons? Like, is this like really a good idea even? Should people keep trying? Is this like idea dead in the water? How do you sort of think about this?
That's a good question. I don't have the answer, so I can just sort of hand wave and have some semi-informed opinions. So I think for higher bit counts, integers were tough because of the real number line sampling issues, right? So if we look at this figure, what's going to happen if you have the same number of bits? The question is, what does your application need? And if you have to represent like large magnitude values, let's say I need to represent, for whatever reason, 300. Then I can do that with integers with scales. I can stretch them out, but then the interval also increases. And then, so let's say, and then I lose, the samples closer to 0. And if my application does need that, then I'm kind of screwed because integers just say, I'll only sample the real number line uniformly because you can only apply a scale factor. And that's where floating point formats have some advantage because they can stretch out to high magnitude values. They will sample those more coarsely, right? But then they'll have representation closer to 0 and for small magnitudes. And we'll look at some histograms later on. So nobody really knows the answer, at least that I know. But my suspicion is that's what causes problems for integers is just, sometimes you have to cover a fairly wide dynamic range, but you still need enough precision to distinguish even the smaller magnitudes. And that's where integers will struggle and some floating point representations will outperform them.
So Dongyan is asking a follow-up question, which is, haven't recent Tensor cores dropped some support for low-bit integers? Does that mean even inference is shifting towards floats?
So it's true. I'm trying to remember the history now because I think Turing. So I think in Tate support, I forget now for the latest chips. Might still be there. But what got dropped was Int4, right? So Tensor cores, I want to say for Ampere had Int4 support. I might be wrong because it's been a while ago. And then there wasn't a whole lot of usage, so that got removed. And there are now low precision floating point representations. So yeah, I would say that if I had to make a choice for inference today, I would probably use on the latest hardware floating point representations that have a similarly small number of bits. Another observation, I don't have that in the slides, but we can chat about it when we get to, let's say, things like FP4. When you get to very few bits representing floating point, things start resembling integers to some extent. They get similar, right? So if we look at 4-bit representations, actually one of the binary floating point encodings basically turns into integer. So let's say E0, M3, I think it's essentially the same as integer sampling at that point. So that loses some of the benefit of floating point because you have so few samples. I'm not sure if I answered. Actually, what was the question again? I guess maybe I rambled on too much.
No, I think you answered it. I think you're mostly agreeing with the question asker. So yeah, we can keep going.
Okay. Yeah. So what are the cons of integers? So the main one is that maintaining accuracy isn't easy, even just for inference, right? So networks are trained in floating point, with some exceptions, which really means that they have fractional numbers, not just integer values. And we can deal with that by adding scale factors. So you can take your integer representation, then have a floating point scale factor, and now you can represent fractions. In the next slide, I'll walk through why you'd want to do that. But to find those scaling factors, now you have to do calibrate. So you have to inspect your tensors to figure out what scaling factor to use. Sometimes you still lose accuracy, so you have to do things like quantization or training, so QAT and so on. So there's quite a bit of involved effort there. And it has been done, but it's non-trivial effort. So a quick note on scale factors, because that again will come up for floating point. So, similar problems arise for floating point as you go down to fewer and fewer bits. So maybe this is overly sort of mathematical or, overly equation oriented. But let's say we have a vector X, right? And so there's a bunch of vector elements, let's say K vector elements. So A sub I would be a scalar. So it's a vector of real numbers and some high precision. And then we want to have, or let's say floating point. I want to have a quantized version of that vector that's in integers. So I'll call that X subscript Q. So that's integer version of that vector. Now I had all those fractions, presumably they were needed, so I still have to have some ability to recover them. So now we have X prime vector. This is really what you get when you take your integer quantized vector and dequantize it, so to go back to real number representation. And the idea is that you have some scale factor. So in this case, it's decode scale X for vector X. And the idea is I'm going to take my vector of integers and I will multiply each integer value with that scale factor. And that's how I decode. So effectively, to encode, you take your real values, multiply with some scale, then round to an integer. To decode that integer, then you convert to high precision and then divide by that original scale factor or just multiply with a decode scale factor. And you get an approximation. And the reason you want to do that for linear operations is because you can factor out the scale factor math until the end of a dot product, right? So if we think about machine learning, much of the time is being spent in matrix multiplies or linear layers. And then we can just look at that as just a collection of independent dot products. They share some data, but that's a sort of a hardware optimization question. But mathematically, if I'm computing Z, which I want to be the dot product of X and Y, then I can actually carry out my multiplications and summation in integer space and only take the final result in what sometimes people will call epilogue of a gem or linear operation, then only convert to floating point and apply those scale factors. And that can be done for linear operations, right? Because I'm multiplying pointwise xq times its scale and then yq times its scale. And since scales are the same for this block of k values, I can factor them out. So everything inside the summation now is just integer values, right? So this is why I can do integer multiplies and adds, and only the final result has to get converted to floating point. After that, you can choose to requantize. So this is really the crux of why integers and actually low precision data types in floating point are being used for neural network math, is because you gain speedups. So this operation is where you spend much of the time, depending on your block size. So the larger this block, the better for speed. And you can do it in some low precision, integer floating point, and only the final result you upscale and sort of dequantize. I'm assuming there's no questions on that, so I'll move on.
I mean, it's a very cool explanation, though, for what it's worth, just because it makes it very obvious that you're dequantizing, like, that you can choose when to dequantize. So I haven't seen someone explain this before like this.
Yeah, the idea, the assumption any kind of integer low precision operation here is cheap compared to, let's say, FP32. So therefore, you do most of your math cheaply. Okay, so quick illustration, and I think that's the last thing I have on integers. So, but illustrates some of the difficulties. This is from one of the papers out of my former group at NVIDIA. So there's two figures ripped out of that paper. What they show is like a histogram of values, and then what happens with different calibrations. So we grab some tensor, and the x-axis is just magnitudes of values, and the y-axis is the number of occurrences of values in a particular bin. So we see it's kind of skewed towards a smaller magnitude. So it's a real number line here. And then there are different ways to calibrate. How do you choose the scale factor? So one way to choose the scale factor would what we'd call, let's say, max calibration, is where you find your maximum magnitude in your tensor, and you say, okay, I will take that maximum magnitude, and through scaling, I want to map it to the maximum magnitude in the destination format. So let's say we're using 8-bit integers. So here, in floating point, the maximum magnitude was, let's say, 2.1, this bin over here, the small blue bin. And then really what I want to do, I want to find a scale factor that will map that value to 127. And I cannot do math in my head, but it's going to be, I don't know, 660 something. So the idea, I'll take my real values, I multiply them with a scale factor, and then my maximum magnitude becomes the largest, let's say, integer I can represent. And then all the other guys going to get dragged along with that. And then after that multiplication, you will round to integer representations. Now, but what you can encounter is that your largest magnitude might be an outlier, and maybe it's not even important. So there are different, sort of scale factor selection approaches. So you can look for, let's say, entropy-based one. So let's say optimize something like KL divergence between your quantized and unquantized. And then that would pick the scale factor based on this value, which basically means that all the values to the right of the green vertical line would become the same value. Since we're talking integers, they don't become infinities, they just get saturated to the maximum representable. So everything greater than, I don't know, let's say 1.45 would become 127 in integer land. Another approach is sort of to do percentiles-based calibration. So you say, okay, I will find a 99.99th percentile of my values, and I'll make that represent, turn into the maximum integer, and everything above that would get saturated, so it just turns into the same value. So you can see, like, you will be sort of saturating more and more values based on different approaches here. And then the table here just shows what happens to various networks. So this paper is from a while ago, so CNNs were all the rage and transformers were just beginning to appear. But the key observation here is that, this column shows the accuracy for FP32, which back then was the native way to train things. And then different columns for different calibration approaches, and the resulting accuracy when you ran inference evaluation. And in bold numbers, we have the highest accuracy numbers for any given row. And what you will see that, well, there's not a single column that has all the bold values. They're spread out, which is a bit unfortunate because that suggests, okay, different calibration methods seem to mesh, differently with various different neural networks. So that's sort of what made it more complicated to use integer quantization, is that there was not sort of a very straightforward mechanical recipe you could follow. You would have to evaluate various things to see what worked best for the particular network. Okay, so that's integers.
Actually, so Paulius, yeah, so one thing I found interesting about this chart, though, is that, like, at least with LLMs, and I don't know if it's because of post-training quantization, but a lot of those models, when they were released in FP16 or BF16, were, like, if you looked at the distribution of weights, it was basically mean 0, like variance 1 already. Maybe this is already, like, that picture that you're showing also seems to be smoothly degrading, but, like, do you suspect, like, people were doing this because they wanted their models to be more amenable to, like, quantization, like, later down the line? Or is there, like, a good like, it seems like here, presumably before quantization became popular, there'd be no reason for people to muck around with the distribution of their weights before releasing them.
Oh, yeah. So I think generally, so again, I'll make a generalization, and I'm sure there's always exceptions. So I think generally people didn't muck around with weights. They just released or used whatever came out of training. Usually you would start mucking with weights and indirectly activations if you wanted to quantize, because then you wanted sort of these properties to where maybe you wanted to reduce the dynamic range, or get rid of the outliers. And there are various techniques that will do that, like smooth quant and others, that will take these tensors and then somehow post-process them, trying to reduce the impact of these outliers. But overall, yeah, I think oftentimes the distributions of weights and even activations appear sort of normal-like in their shapes, so you kind of get bell curves. It's not always true. So for example, where that tends to be not true is for activations whenever you add the skip connection values, right? So let's say, I don't know, Leonardo produces some values and then you add a pointwise a tensor that comes through a skip connection. You can actually get these sort of like doubly humped distributions and things like that. So it's not always a normal looking distribution of values. And then I have more histograms of these things, and it's tough to really gauge from them what's needed, because this outlier may not be needed at all. And conversely, we've seen cases where errors on large magnitudes had a more significant impact on, let's say, evaluation accuracy. And that's part of the reason the way we choose scaling factors. We try not to saturate a lot of large magnitudes, especially for training, because we've seen training accuracy suffer more from that. So yeah, there's not a good answer to that. But I think generally, unless you're quantizing, you don't care much about the shape of your tensor distributions. And when you're quantizing, it's not necessarily that you're trying to fit into a particular curve shape. The histogram, like many times, you try to reduce the required dynamic range. So sort of the delta or the ratio between the largest magnitude and the smallest magnitude that you need. These distributions here, my personal take is they probably matter less than the range that's required.
So I'm going to say that
I would be wrong. Yeah.
So I'm going to say something that's probably wrong, but like maybe will lead to an interesting discussion, which is that like it seems that like that sort of the local LLM basically trend like around like Llama 2 and all those related models, like those models were like really amenable to quantization because it's like to your point, like there's no skip connections, there's no crazy dynamic behaviors. It's all like linears and some like simple non-linear linearities. So that's like basically a quantizer's dream. And presumably, the more complicated architectures become, the less you can make, the more likely you're going to see jagged shapes in your weight and activation distribution, which is going to make those models harder to quantize than something like a bunch of dense linears.
Perhaps. So even llamas do have skip connections, right? That's a pretty common thing in transformers. It's just sort of like the skip connection is kind of when you route a tensor, around the attention and those things, and then just do the weighted. So that does come up, and we've run into that, challenge where, those tensors were tougher to quantize. Yeah, so I don't know. It's a good question how that relates to network complexity. So certainly, and I think I might have a slide later on that shows that, larger models sometimes are easier to quantize, so they, suffer less from quantization. And there will be different schools or, of thought trying to explain that, right? So one aspect would be that, okay, well, maybe those models are more over parameterized, so therefore they can take more damage before really losing accuracy. But that hasn't been fully established. There are some papers on like scaling laws and precision, but it's still a pretty active area of research and investigation.
Sounds good. Okay.
Cool. Okay, so moving on to floating point. All right, so mostly it'll be a IEEE-like floating point that we're talking about. And I was trying to come up with sort of like slightly gentle introduction because you can spend, a couple of hours just on intricacies of this. But anyhow, so we already saw that it samples the real number line differently. And unlike integers, so a IEEE floating point has several bit fields. So you'll often see me refer to the notation that's EXMY or XME. So E stands for exponent, M for mantissa, that's just different fields within representation, and X and Y is how many bits we spend there. But there are really 3 bit fields. So usually there's a sign bit and a single bit for that. 0 indicates positive number, 1 indicates negative, right? So this is the going back to sign magnitude representation idea. Then you have exponent bits. So we'll have E bits of exponent. And exponent is really just a power for a power of 2. And it's represented as a biased integer. We didn't touch on those, but basically bias, and I'll give the formula here. It's not super important how it is, but the idea is that if you look at the exponent bits and just interpret them as an integer, they'll be between 0 and some value. So let's say if we look at FP16, which is an example I have here below, 5 bits for exponent. So 5 bits can take on values between 0 and 31 if you just look at them as an integer that's not signed. And then the idea is you will subtract the bias from that encoding, and that's how you actually get the real exponent. So maybe I'll come back to that when we look at the example. Anyhow, so you have some exponent bits, and they largely define the magnitude of your number and largely affect the dynamic range. Then you have mantissa and M bits. So mantissa, again, that's actually not IEEE terminology, but it's a very popularly used word. It's the fractional bit. There's always an implied 1 bit unless you're dealing with subnormals. So as you can tell, with floating point representation, there's a lot of intricacies. And so handling it properly and fully becomes trickier and trickier, let's say compared to integers. But fractional bits, again, they're sort of positionally encoded. So the first bit corresponds to, if it's 1, then you multiply with 2 to the negative 1. If it's 0, then same idea. And if it's second bit is set to 1, then it indicates a quarter, or 2 to the negative 2, and so on. But it's easiest to just walk through an example. So I picked like a smaller representation, so one of the FP16s, so E5M10, that's FP16 representation. That is an IEEE, actually. I think that's the smallest data type in IEEE today. So 5-bit exponent, 10-bit mantissa, 1 sign bit. So that's how you end up with 16 bits. Exponent bias is 15, just applying that formula from above. And then I just picked some value here. So there's a binary string of 16 bits, and it decodes to 6.5 in decimal. Right, and the way to do that, so we have 5-bit exponent, and so 10001 is 17 in binary. So that's how we have 2 to the power 17, but we have to subtract the bias. So that's in purple. So that's how really it's 2 to the second degree. And then you multiply that with a significand in IEEE terminology. And the significand is really the implied 1 bit. So that's the thing in red. And then after that, you have the fraction. I dropped all the trailing 0 bits. And this is in binary, right? So this is 1, but then we have the first bit set to 1. So that's 2 to the negative 1. Next bit is 0. So there's no 2 to the negative second contribution. And then the third bit is 1. So that's 2 to the negative third. And once you add these guys up, you get 1.625 now in decimal. And then you multiply that with your sort of exponent contribution. So that's 4. And that's how you end up with 6.5. So that's how you look at the sort of IEEE, or IEEE-like binary string, and decode it. And encoding is just sort of like the reverse of that process.
So Paulius, like presumably, like our ancestors had fierce debates around like how to design these initial floats, like whether it be, why not like FP17? Like I don't know, maybe multiples of 2 are nicer, but like why not 4 exponent bits and 11 mantissa bits? Could you maybe speak to like how these things get argued for? Because I think for the MX formats, maybe it's a bit easier because it's all AI data types, and you can look at LLMs and make arguments here. But this is a bit, to me, seems much harder to make an argument for one choice versus another.
Oh yeah, so I think so the history of this really predates me, but I think so a IEEE standard, I want to say, came about in the 80s, maybe late 70s. I might be slightly wrong there, but it's been around for a while. But prior to that, there were computers doing arithmetic for a long time too, for a few decades. And there was, floating point representation was kind of Wild West. Various vendors, hardware vendors, had different implementations. And I think Khan was Intel, I want to say, and IBM had different implementation, and so on, various mainframes. And it was done mostly for scientific computing. And at some point, folks decided that we need to have a standard encoding, so we can actually, port our code and have some kind of reasonable expectations for numerical behavior. So that's how our IEEE effort started. And from what I understand, it was actually, quite debated, and it was not a unanimously agreed upon solution, but that's what sort of the majority agreed to, and that's what became the standard. I don't know exactly what they used to evaluate, but I think they looked at various, so I think kind of did a lot of work based on just sort of fundamental principles. And then, there was some testing on applications, and that's how single precision and double precision came about. And FP16 was added later on. I think that was done in early 2000s. And that actually came from the graphics world. And I think that goes back to NVIDIA and ILM. So that also predates my time at NVIDIA. But I think that was for high dynamic range imaging. People wanted to go beyond 8 bits to represent colors. And then they went with floating point-like representation back then. Again, just to have this ability to have a wide dynamic range to represent both very small magnitudes and large magnitudes, and just sample the number line differently. And I think back then, for the graphics purposes, they arrived at this E5M10 representation, and hardware got made, and eventually IEEE adopted that. So that's kind of the history behind FP16. It sort of came from the graphics world, and then conveniently it started getting adopted for AI. And as we'll see, there were some difficulties would pop up now and then, and that's how BFloat 16 came about.
But that's interesting. So basically, different like different people interested in floats would effectively need to lobby, basically. Like it's like, you know, the
Yeah.
graphics obviously now the AI lobby is like dominant, but like that's like sort of maybe the right way to think about it. And then you have like tons and tons of applications, whether it's like people doing radar or like aeronautics or graphics, and then they kind of argue out, and then the applications that went out basically get dibs on how the floating points formats get designed.
And a good example of that would be FP8, and I have that I think mentioned later on. There are different FP8 encodings. There are actually a lot of them, and it's kind of a funny thing because when you think about it, it's only 8 bits. You know, how many different choices can you make? But you can make a lot of choices. And so there's an IEEE working group trying to standardize FP8. The only catch is that working group, I think by now, has been around for 3-4 years, and it's been so slow that no conclusion is being arrived on. There's a lot of debates and evaluation of data, and that's gone on for so long that people start moving beyond 8 bits to like 4 bits. So that's how OCP standard came about, because then a few hardware vendors got together and said, look, well, our representations that we may have are somewhat different, but we need to have an encoding just so we can exchange checkpoints and just have the software function. So let's just standardize some encoding that we have a spec to which we can write software. And so that's how OCP format came about. And the formats are not necessarily perfect, right? And it's hard to say what would be perfect for various scenarios. And that's where people debate, positive and negative zero merits, and then what exponent bias to use, and so on. And at some point, you just need a practical solution, because a lot of that becomes, to some degree, philosophical. And at some point, you just need to have a definition to follow and just work with it. And then maybe I'll come back to this question later on when I think I have a graph that shows posits, right? So that's kind of interesting because it is like a representation of real numbers, so fractions, but it's quite different from IEEE floating point, right? So in that world, you have, Kahn, and then there's John Gustafson, and they have quite different views on what number representation should be. And, those debates get heated and exciting.
Excellent. Okay, let's keep going.
All right. Okay, so floating point sampling. As I mentioned, I guess, exponent bits sort of define which powers of 2 are sampled on a real number line. So for FP16, exponent samples are between 2 to the negative 15 and 2 to the 15. In reality, it's wider than that because of subnormals. I'll have a bit more on that later on. So that's what really largely determines your dynamic range. I think dynamic range I have not defined, but that's the ratio of your largest representable magnitude divided by the smallest representable magnitude. So for FP16, that dynamic range is roughly 40 powers of 2. If we look at FP32, I think it's like 200 something, 240 or so powers of 2, so much wider. Then mantissa bits define your sampling between successive powers of 2. So that's your precision. Right? When people say single precision, double precision, to be pedantic, that really just refers to the mantissa size. But if you look at E5M2, 10-bit mantissa bits, therefore you have 1,024 samples between each power of 2. If we think about bfloat 16, which is also 16 bits, but that's E8M7, right? That has a smaller mantissa, only 7-bit mantissa. So bfloat 16 only has 128 samples between each power of 2, but it has a wider range. So that makes a different trade-off. And the key observation that I think I've mentioned a couple of times is that floating point samples that real number line with equal intervals between successive powers of 2, as opposed to integers. And you'll have the same number of samples between, a quarter and 5 as you have between 128 and 256. So unless you're looking at the log scale, your sampling of the real number line sort of gradually becomes coarser and coarser as you go to the larger magnitudes. So we've seen this illustration, so I'll just skip through it. But yeah, this sort of shows us, higher density towards 0. And a few more details. So that's where I'll get to special values, right? Again, integers usually don't have these. So there are a number of special values there, which are really reserved bit patterns. And those usually follow sort of exponent special encodings, either all zeros or all ones. So zeros in IEEE have both positive and negative zeros. And that just means that all exponent and all mantissa bits are set to 0. And then the sign bit can make it a positive or negative 0. So again, you could view that as losing one sample because now you have 2 encodings for the same kind of value algebraically, or the same point on the real number line. Subnormals, okay, those are special values. exponents are all set to zeros. Mantissa bits are non-zero, and I have a slide on that coming up. There's infinities, both positive and negative, so that's what you will get when you overflow. You generate a number that is larger than you could represent in a particular floating point format, then usually it'll just generate an infinity pattern. You can actually do math with those. They'll tend to propagate. And then you have nans, or not a number. So those actually will have a bunch of encodings in IEEE. So 2 to the should be m minus 1, I think, bits. Oh, no, 2 to m plus 1, because there's both positive and negative. So as many bits as you have in Mantissa, that's how many encodings you will take away. So exponent bits are all set to ones, and then Mantissa must have at least one non-zero in there. And these are generated by things like square root of a negative number, sum of the positive and negative infinity, where just you cannot do any more math. So usually they'll signal something bad happened numerically. And there are signaling, non-signaling names, but they're not that relevant to us. But the key thing to recognize here is that infinities take encodings and nans take a bunch of encodings, and that's where subsequent formats that are not like that are IEEE like, sometimes they will give up some of these encodings in order to recover samples to sample more of the actual real number line. That will happen as you go to fewer and fewer bits. So FP8 started to do that. FP6 follows that. And FP4 does it even more. Because as you have fewer and fewer bits, you want to reuse, you want to waste fewer and fewer potential samples on the line. So a quick note on subnormals, maybe I'll just rush through that in the interest of time, but it's a special interpretation of exponent bits, as I mentioned, and basically just says that exponent, you just treat it as always being just -14. And it gets rid of the implied 1 bit in the significand before the binary point. So just as an example, quick illustration of a number, right? Just as we saw in a couple of slides previously. So my exponent is all 0 bits, and Mantissa does have non-zeros. Therefore, this makes it a subnormal number. And then the decoding is that I see this pattern, and then so exponent becomes automatically -14. And now in red here, for normal numbers, you would have the implied 1 bit. So for subnormals, there's no implied 1 bit, it's a 0. And the rest just proceeds as before, so you decode it. But the key here is now, since there's no leading 1 bit, I can have small and smaller magnitudes that are defined by how many leading 0 bits I have in my Mantissa. Right? So one way to look at subnormal that is really, in this case, the most significant bit is 1. So logically, so we normalize it. So we multiply by 2 in order to move that 1 across the binary point. Then I have to adjust my exponent down by 1. So it's really the same thing as 2 to the -15. And then I can do sort of like a really more traditional IEEE like decoding math here. So that's how you end up supporting, smaller and smaller magnitudes, right? And really the purpose of that is to, waste less of the bit space that you have. So you can make use of the Mantissa bits even when your exponents are all set to zeros, right? Because usually there's fewer exponent bits. So once you run out of those encodings, you can still recover these guys to represent smaller magnitudes by having more and more leading zeros. So some hand waving about that here, but that's, folks can take a look at that. But I think it's interesting to look at that visually, right? So I'll have a few of these graphs. So the way to look at these is that on the x-axis, I have the exponent, or just think of it, I have some value x, and I take log base 2 of that. But these would be, let's say, exponent encodings. And this is for FP32, so that's why it goes all the way up to 127, and then it'll go down to pretty small values. So for FP32, your exponent will go between -127 and 127 and I think -127. And you see that for all of these exponent values, so the y-axis shows the precision on number of samples between powers of 2. FP32 is E8 M23, so in this region you just have 23 bits of Mantissa or 23 bits of precision, no matter what power of 2 you have. And this sort of follows the definition of floating point, that same number of sample points between successive powers of 2, except for once you get to subnormals. So all of these guys on a slope, now they have all the exponent bits set to 0, and they just end up having more and more leading 0 bits in the Mantissa. And because of that, you sort of like your precision is only the bits after the first non-zero. So as you go to smaller powers, you have fewer and fewer remaining mantissa bits to encode. So that's how at the very end you end up with just one value there. So this is sort of a good way to look at some number representation and say, okay, so this is the dynamic range or the range of values, and this is the precision. How much precision do I have for various magnitudes? And floating point has, full precision for most of the range, and the subnormals will gradually have less and less and less precision. So any questions on this graph? Before we look at a bunch of these, I guess let's make sure that folks can really follow it.
I think this is clear. I had a slightly unrelated question, but one thing I noticed is like people spend usually like when people are explaining floats, you typically spend a good amount of time explaining like the encoding, but then there's also like I think the IEEE standard also describes like semantics of ops on those floats. So for example, things like what happens if you take the max of a value with like, let's say a positive or a negative zero, like what should you expect the output to be?
Yep.
So my question here is that like, I found it really hard to figure out like what are the exact semantics that NVIDIA likes to follow. Like for instance, it was very difficult for me to get like a piece of CUDA code to output the negative zero. Like it was just much easier to output like a positive zero relative to CPU, which caused some inconsistencies. How come? Like basically, we have standards. Hardware vendors just don't think it's important enough to publish this. They are worried people will copy them because their approaches have better performance characteristics. Like what's going on? Like why is this?
Oh, okay. Yeah, very good question. So I think NVIDIA and AMD GPUs, and I suspect other chips, when it comes to single precision floats or FP16, if they claim that they're IEEE compliant, they will implement whatever the standard requires. So if we pick, let's say, on FP32 or FP16, which are defined by IEEE, so on NVIDIA's hardware, those scalar operations, and I'm emphasizing, so basically non-tensor core, so whatever happens in CUDA core, is IEEE compliant. So you will get the, IEEE defined negative and positive zero treatment, same thing for infinities and nans, right? That are like strict rules on how operations that involve nans and infinities operate and what values they produce. And I think vendors just don't publish anything around that because the implication is that it's just whatever's in IEEE standard. So get the IEEE standard, and whatever you see there is what you will get out of hardware. Zero, positive, and negative is an interesting thing. I actually got bitten by that recently, where I was trying to generate, negative zero and write it to memory, sort of a Lamport style flag. And, my code was hanging. And then I discovered that even though I'm writing, in C++, I have a literal negative zero. But then I discovered that what gets written to memory, I think was just a plain zero. And, or maybe when I was doing, maybe I was doing comparisons against negative zero, and I could never pick that up. And then I looked up in IEEE standard, and IEEE standard says that for comparison purposes, negative zero and positive zero are the same. And what the compiler was generating, so even though in my code was checking, is x equal to negative zero. If I looked at assembly, and assembly was just checking is x equal to zero. But that's completely IEEE compliant behavior, right? And that check, I guess, technically would have still returned the same true or false value, even if I had a negative zero there. So I had to change, my code to actually use a binary pattern for negative zero and just do integer testing against that. So that's sort of a quirk that might be interesting to folks. But yeah, so like when it comes to single precision or half precision FP16, if they are IEEE compliant, you can just look at the standard, and the hardware should just have that. And if it doesn't have that, that would be, a surprise to many. Now, if you look at things like tensor core operation, that's where, IEEE only defines operations on scalars, including fuse multiply add-on, which I'll touch sort of at the end a little bit. But when it comes to dot products, it's completely a Wild West today. And those implementations change in hardware from vendor to vendor, also from the same vendor, across chip generations, because people keep tweaking implementations, making dot products larger, and so forth. So those are basically, implementation choices by a particular chip, right? So TPU does one thing, NVIDIA GPU does another thing, AMD GPU probably does something slightly different, and everybody's trying to invent something that's more efficient in terms of area and power consumption. So that's non-standardized. I don't know to what degree I've answered your question, or
I think you did. I have another like meaty question, but maybe
yeah.
I'll wait until you cover MX formats or some of the
Okay.
ML stuff. But yeah, like I'll stop
Sure.
myself.
I'll try to get to that sooner. Okay. Anyway, so this is this graph, but it's interesting to look at when comparing different types, right? So same graph, but for 16-bit formats. And again, as I mentioned, there's two of them. So there's FP16, which is IEEE defined. So that's E5M10. It's in red or brighter red. So we can see it has a narrower range. So on the x-axis, it covers fewer powers of 2, but it does have 10-bit mantissa. Therefore, for much of its range, it actually has 10-bit precision, and then it sort of gradually drops off. Bfloat 16 is sort of the maroon or dark red color here. So it's E8M7. So its exponent is larger. It's 8 bits instead of 5. So we can see it covers a much wider dynamic range, right? It's almost as wide as IEEE FP32. But to cover that, it sacrificed mantissa bits, so it'll have less precision. And where that precision matters or doesn't matter, it's very application specific and so on. Going smaller.
Actually, could you go back to the other picture? Like it is remarkable when you interspace them like this, like how dramatic the difference is. So I've heard from a meta colleague, and I'm hoping you could give us like also maybe a war story here that like apparently like NVIDIA wasn't too happy that the Bfloat 16 format became very popular, primarily because I think it was like a Google format, whereas FP16 was already supported in the hardware. So why would this be annoying if you're like a hardware vendor? Is it you just like need completely differently designed hardware? Do you need completely different design compilers, or is it just like a minor inconvenience to go from like let's say accelerating FP16 to BF16?
Oh, I guess from my point of view, I wouldn't. I don't have a recollection of NVIDIA, being annoyed at Bfloat 16. So Bfloat 16 certainly made things easier in many aspects. It just sort of like if I think about how that happened historically. Single precision was around in hardware. And then even before tensor cores, NVIDIA already had some FP16 hardware for graphics, right? So they were vectorized operations for that. You could get twice as much math throughput. One catch is that they actually were producing FP16 outputs. They would not produce FP32 outputs, which was a bit of a problem, and that's what tensor core solved. So that just got adopted, and software got written and shipped, so people could actually take advantage of the format that was already in hardware. And we had to solve a bunch of things, and I have a bunch of slides that sort of show the history of that, how we solved various problems. And the idea was, well, it's a format that's been in IEEE as a standard for 10 years, so let's just use that and see if we can make it work. In the early days. And then Bfloat 16 came out. It did come out of Google. I think originally they even used it just as a compression approach, like a lossy compression, just truncate the bits off and like for network communication.
Oh, yes.
Right. And that worked well enough. And then so from NVIDIA's point of view, I can't really speak on their behalf. I'm no longer at NVIDIA.
Oh, but, so for BF16, you're saying you wouldn't even need hardware support to see acceleration because of this like chopping aspect, because you have the same dynamics, you have the same exponent as FP32. Yeah. So it's just easier to port existing code. I see.
Well, so I think if you just treat it as a lossy compression, and another thing is if you would just chopped off the least significant 16 bits of mantissa, that certainly work, and it would be fast to do that. The question is, do you need a more proper rounding, right? Because that just would always round towards 0, right? And it could create problems potentially in some cases. So that could accelerate things that were purely bandwidth limited, or where you're trying to save memory footprint. It would not accelerate your math because back then there were no math units that would do that. So you would have to pad and then just do single precision math. So it was basically acceleration of bandwidth limited cases, which makes sense for communication and other things like that. And then Bfloat 16 units got added to hardware, right? So NVIDIA added them, TPU had them. So from NVIDIA's point of view, historically NVIDIA never has been really married to a particular data type. Like NVIDIA just wants to ship things that are useful for people and for various applications, and whatever they are, that's what NVIDIA ships. So that's why NVIDIA started supporting Bfloat 16, basically with a chip generation after Volta, and has shipped that since.
Yeah, like as soon as they could, they supported it. Yeah. Basically, like one generation.
As soon as it was clear that it is a format that actually works pretty well. And you can see because of this dynamic range, it did make things easier. So war story wise, in training, there's a lot of these epsilons that happen, right? So if you think about even things like batch norm or layer norm, whenever you take a ratio of something, usually you'll have an epsilon in your fraction to prevent divisions by 0, right? And people would just arbitrarily pick some small magnitude, I don't know, e to the -6, e to the -10 or something like that. It was intended to be very small to not impact anything, which in MLPerf later we discovered they actually do impact convergence in some cases. But then a lot of those values were so small that they would just become zeros in FP16. So you had to be careful when converting your training scripts to FP16, to pick some value that would not get flushed to 0, because then you would get divisions to 0 if they get flushed to 0 and things like that. But with a wide range that bflow 16 has, you don't have to worry about those things. You had to worry about things like where you needed more mantissa, but that's somewhat rarer. Okay, so going smaller, we got to 16 bits. And I think I have a slide that says, okay, BF16 training has become sort of the standard for quite a while. Okay, then there's a desire to go smaller. So FP8 formats, there's 2 of them. I'll touch briefly later on why there's 2. E4M3, E5M2, so different just sort of encodings of the same number of bits. And not unexpected, E4M3, smaller mantissa, so covers narrower range on the x-axis, so fewer powers of 2, but has more precision. E5M2, wider range, but sacrifices precision to achieve that range. And if we look at all of them together now, I even threw in here, E2M1, so that's a FP4 format. You can see how tiny that thing is compared to FP32, where machine learning started. So that's kind of like, it's an interesting sort of representation of the different dynamic ranges and precision, and how far we've come along. Now, going this small does have cost, right? So you cannot just use values out of the box. Scale factors come about, and scale factor granularity becomes a question, and we'll touch on that briefly. So this is one slide that I alluded to. So what's interesting in this one is the green curve, right? So these are different 8-bit formats. So the blue and yellow are FP8 formats that are in the OCP standard, as we saw in the slide earlier. Green is a posit, right? So that's sort of proposed by John Gustafson. As far as I know, there's no hardware implementations of that, and it's not obvious whether it's better for some applications. It does have interesting properties, but you can see that it actually samples the real number line quite differently, right? So IEEE-like representations, sort of full precision for a while, and then they gradually decay towards the left. Whereas posits, they're centered at 1, first of all, not at 0, but then they're sort of symmetric. So smaller magnitudes and larger magnitudes both lose precision as you get away from further and further away from 1. So just a different, it actually has 2 arguably exponent fields in it, and then uses run length encoding. So if you just Google posits, you can find it. Yeah, go ahead.
But it makes intuitive sense, though. Like, I'm looking at this, I'm like, oh yes, why would I need to be precise for massive values? Like, it sort of makes sense. So like, if you were to guess, like, how come this never made it to hardware? Is it just that like the software applications weren't really there, and the not enough case studies?
Yeah, so it's fairly new, right? And it hasn't been proven out. And depending, I guess, on what paper you read, they will either claim that it makes a difference or that it doesn't make a difference. And there's a paper a few years back from Jeff Johnson, which was really interesting, where he looked at different representation of numbers. It was basically a log format, but for exponents, he was using posit encoding. But once he jumped through all those hoops, it just sort of came about that, 8-bit representation using that encoding versus just plain integer 8-bit encoding. They effectively had the same quality at the end of the day when it came to network accuracy. And then silicon cost-wise, they're also similar. And so I think when sort of studies go deeper into what the benefits and where they would be, oftentimes I think it's found that, okay, it's not substantially better to warrant like pretty different hardware implementation. But who knows? Its day might come. It's hard to say. But I figured I'd include it because just so folks get a perspective, there are different ways to encode real numbers than just IEEE-like formats.
And is there a good intuition, like when, like presumably, like over the years, you've seen many different like D types come and go. Do you have like a good intuition when someone proposes a D type to you to think about, okay, I think this could run efficiently on hardware versus not, or like, yeah, is this like actually like a lot of work to figure out? This is
So I don't have great intuition for that since I'm not an ASIC person. I was sort of more in the numerics end and sort of performance. But yeah, I think there are ASIC people who design the circuitry to do the math units. I think those folks have pretty good intuition, or you can fairly quickly say, okay, this would be more complex or less complex. I'm just not one of those people.
Yeah, no, I mean, like, presumably you walk over to one of your colleagues and ask them, is this a terrible idea or not? But yeah, that makes sense.
Yeah, like, so yeah, when you earlier mentioned the various formats that NVIDIA has contributed to, it's always been a collaboration between sort of algorithmic people, application people, ASIC people. Yeah, a lot of people get involved in these. Okay, so that was the basics. Took a while. Okay, so brief journey through AI numerics history. Okay, so what sampling is actually required, right? We saw different sort of distributions of representations, but what does AI need? And the answer is in the first bullet. Unfortunately, we don't know. We'd love to know. It's not even $1 million question. That's if you know the answer to that question, it's worth billions. But there's a lot of interest in reducing the bits per value, and that's understandable, right? Because the smaller your representation, the less memory footprint you need, which is a good thing. You can fit larger model, more activations, in your memory. It reduces memory bandwidth pressure, right? So when you have to access that memory, also you have to move bytes, right? So the fewer bits you have to move across memory buses, the less energy you need, so you save power. Power is becoming extremely important nowadays for performance. And low precisions per operation do require less energy. It also enables packing more math units into the same silicon area, right? So you can get more effective memory bandwidth utilization per value if your value is smaller. You can also get more math ops out of the same silicon, nanometers. So a lot of motivation to go smaller and smaller, right? What works, what doesn't work is largely empirically driven, unfortunately. So these studies get pretty expensive, right? But effectively, you run various studies, and those inform and evolve your mixed precision recipes and formats, right? So if we look at the history throughout time, we started with FP32, and I'm looking at like recent history of machine learning, right? So let's say starting, from 2010 or so. There's decades prior to that, but in sort of this latest wave of AI studies, it was FP32 initially, then went to 16 bits, which were, I would say, even today, are still largely used. FP8 is becoming more and more prominent since hardware has been around for that now for a couple of chip generations, and people are beginning to adopt. And there's early sort of ventures into FP4, even for training. And I put FP6 in the parentheses because it's sort of like a halfway point between FP8 and FP4. Okay, so
but one thing that always seemed, and correct me if I'm wrong, like one thing that always seemed bizarre to me is that like it's one of those rare situations where the hardware people are bolder and ahead of the software people because they're shipping dtypes that they're betting that the community will figure out how to have stable recipes for. And maybe they'll do some a priori work, but like this is quite strange to me because you would expect typically hardware people to be a bit more conservative. Otherwise, like let's say if they pick the wrong dtype, then all of a sudden, that whole hardware generation is like dead in the water and won't sell, right? So the cost is quite high to getting this wrong.
Oh yeah, so the cost, you're absolutely right. The cost is high, right? And I think different hardware vendors have different tolerance for risk here, and bet taking. So I'm obviously biased given my past, but NVIDIA generally has been pretty bold at trying new things, and also spends quite a bit of resources to evaluate those, right? So like whatever goes into hardware, from design to the shipping of silicon, quite a bit of time passes. And so during the design phase, we would try various things and see how well they work. And the most promising ones would sort of make it into hardware. So there would be recipes tried out on a much smaller scale to sort of inform the direction for hardware. And then as we get closer to close in shipping, then, larger and larger scale training runs would get run. And then eventually when silicon is available, you can do really large scale executions, right? Because like all of these studies do sort of like simulated precision, right? Because the hardware doesn't exist, so you have to somehow process your values to where they behave like what you might have. That adds quite a bit of overhead to your experiments, so they become pretty expensive. And neural network training at scale is expensive, so it's a non-trivial cost. But yeah, that's why I think sometimes you will see vendors who are more aggressive, they'll kind of lead the way, and then others sort of follow and adopt what they had seen work. But to a degree, if you don't try something here, I think you'll just stagnate, right? Because through sort of like end of Moore's law and other things like that, it is hard to keep improving dramatically performance of, let's say, single precision floating point type. So you can hit that wall. So you have to actually go to something smaller.
But if the argument is based on simulation, then arguably we should know from now what's likely to be the lower bound and smallest like dtypes that we could use. So for example, like I've heard some people speculate that that's after FP4. Other people say no, there's also the sub-bit types. So like this has a lot of stuff to squeeze. Did you have any hot takes you'd like to add on this topic?
Well, I'm one of the people that say that sub-bit types theoretically are possible. How well they will work, it's really hard to say. And I think I have just one slide that just mentions that, but basically, all of that would be some kind of lookup table based thing where you're counting the index bits, but then what you're storing in a table is higher precision, right? That's how on average you end up with fewer bits per value. It's really hard to say, right? Because these studies, it's hard to have very definitive results, because you can study and prove something out at a smaller scale and sort of gauge maybe potential for success, but then something might come up, right? That happened with even with FP8 recipe, right? Like there was a recipe that was fairly conservative, had per tensor scaling. It worked fine for a couple of years, and then models got somewhat larger, and the data sets got a lot larger, and then a recipe had to be adjusted. So it's sort of a dynamic world where even once you have something that works numerically, you might have to adjust it as if the data sets shift, or let's say model architectures shift, and then just kind of change how they generate values. Yeah, so that's very difficult to answer definitively. You could do that in theory if you wanted to throw a bunch of compute at it. You take the leading models today, and you say, you know what, I'm just going to rerun those training sessions with all kinds of format choices and see what holds up. But then, another aspect of that is you try some exotic format, it will need some extra bells and whistles to work, right? So then you have to really study those to see, okay, how do you choose different scalar factors? At what granularity you need them? So it becomes a pretty expansive space to explore. But,
makes sense. Okay, yeah. That makes sense. Thank you, Paulius.
So, we looked at the sort of these graphs of value representations in formats. This is actually a histogram of values in tensors during training. So I forget actually which network it is. It's either Mascar CNN detector or SSD object detector. So from quite a while ago. X-axis here is just C++ hex notation for floats, but just think these are powers of 2 that we're showing, right? So just look at the number after P, and that's the power of 2 bin. Y-axis is just percentage of values. And the way this was sampled was actually, we looked at all the tensors. We categorized them into weight gradients, activation data, and activation gradients. So those are the different colors. And then throughout training, I think every few steps, we ran through all the tensors and just binned them. And that's what you're seeing here is really bins filled out by all the tensors over a training session. And interesting observations here is that, like, in red are the highest magnitudes. It's most to the right, and that's activation data, basically, right? So you got activation values. Activation gradients are in green, and those are the smallest magnitudes, right? They're most to the left. On the very left here, this big bin is just zeros, right? Because this was a CNN, so it had ReLUs. And then we have weights in blue, right? So they're sort of second in magnitude, sort of between red and the rest. And then we have weight gradients. Those are in black. And again, so that's the histogram here. So you can see the different tensor types actually do end up being in different magnitude regions. But that's just sort of a curious observation. And you can see sort of their shapes, which unfortunately does not really indicate where you need the precision, right? Because just like say that this bin is the tallest for blue, it doesn't necessarily mean that that's where you need the highest resolution or most precision, right? Again, we tried various things, but nothing is that straightforward, unfortunately. So looking at FP16, right? So FP16 has a narrow dynamic range, and this will illustrate why that was an issue. And some folks might have seen these slides, I don't know, 10, 12 years ago. I stole them from, I guess, my own GTC presentations. So these actually graphs are from FP32 training. And for unknown reason, even to myself, I chose not to use uniform width bins. So if you really squint and look at these bins, mostly there's 3 powers of 2 until I get to smaller magnitudes, and I just up it to like 10 and 15 powers of 2. So they're not uniformly sized, but that's not the key thing here. Anyway, so blue are weights, green are activations, activation gradients are black, and weight gradients are red. So we kind of see where they're positioned on this log scale. So magnitude-wise, as we saw before, activations tend to have the highest magnitudes. Activation gradients have the smallest magnitudes. They're most to the left. Those are in the negative range for exponents. Same collection as I mentioned before. Now in blue, I'm highlighting the region that FP16 can represent. So if we look at these histograms, weights have no problem. All the values that occurred are well within the blue region. Same thing for activations. Largely the same thing for weight gradients. These bins have a few values here just outside, and in practice they didn't matter. You can flush those to 0. Activations very clearly do have quite a few values that FP16 cannot represent without anything, right? So those would get flushed to 0. Anything that's outside the blue region to the left would get flushed to 0. But another observation is that much of the FP16 region is not being used at all, right? So if we look at the gradients, so the red and black histograms, the orange region FP16 can represent, and it's quite a few powers of 2, right? So it goes from, I don't know, let's say -2 all the way up to 215. So lots of powers of 2 binates that are not used at all by the gradients. So they're kind of wasted. So the solution for that was, once that was observed, was, well, for gradients, if we multiply them with some value, with a scale factor, they will shift to the right. So if you find a scale factor, you multiply your loss with a scale factor, then by chain rule, all of your gradients, both weight and activation gradients, just get scaled by the same value, right? And we just picked that value to be a power of 2, so mantissa bits don't get touched at all, just exponent bits get adjusted. And that effectively moves your activation gradients well into FP16 representable range. Now you don't lose values and you can train. The only catch is that, prior to doing weight update by the optimizer, you have to undo the scale, right? So you have all the right magnitudes when doing weight update. And that works fine for the most part. I'll get to some difficulties there. The reason you have to do this, so this is always an interesting figure to look at. Oh, I just have some garbage here in the text. But this is a training of a 2-layer LSTM network. That was a big network back then. That was expensive to train because it took a couple of weeks on a couple of dozen GPUs. Those were the nice days. So in orange, so blue curve is FP32 reference training session. In orange is FP16 training. So Volta was the first GPU with Tensor cores for FP16 with no scaling. So scale factor was basically 1. And we can see that it trained fine for a while, matched blue, and then it just decided to diverge. And then in green is what happens with correction when we actually implemented the loss scaling approach, to where you multiply the loss with some scale factor, and that moved the gradients into representable range for FP16. So that's the green curve, and that matches the blue, and that's just a zoomed in version of that, where you can see, even if we zoom in, those curves are tightly intertwined. We actually trained FP16 longer than we trained FP32 back then. So that's why without loss scaling, you flush too many values to zeros, bad things started happening.
And so, Paulius, presumably if you go back to so like right at the point when the orange curve starts to diverge, is that like when activations become too large? Like, just because you had such a nice visualization, and I'm curious, if you were to look at the picture in the slide before, at that point in time, right before the divergence, what would you see?
Good question. I don't know. We didn't look at that.
I see. Okay.
But I would say, based on some other histograms that I looked at, usually what happened is that I didn't see much shift in the histograms throughout training, right? And unfortunately, I don't have those videos, but I had them when I was at NVIDIA, right? So there's sort of folklore belief that if you look at your weight gradients, that they should get smaller and smaller in magnitude as you train, because your loss is getting smaller, your network is getting better. And intuitively, it makes sense, right? Because if your network were perfect, then your loss would be 0, your gradients would be 0. So therefore, if your network is improving, your gradients should be getting smaller and smaller. But in practice, that's rarely the case. So what I've seen, for the most part, there are some exceptions where for some tensors, gradients would get smaller, or weight gradients, but that was very rare. For the most part, what happens from random initialization to like the first few, 100 iterations of training, you would see the shift of those histograms, simply because I guess the random initialization was not in the right space where I guess it should have been, and that's what training corrected fairly quickly. After that, those histograms largely remained in the same place. It was just, different values would take on, or different tensor elements would take on different values. But overall, histogram-wise, it was largely in the same region and didn't migrate. So I think to your question, I would hand wave maybe a hypothesis that overall activations didn't really shift. Is just that because you were fleshing gradients to 0, like a lot of smaller magnitudes, somehow they sort of guided you into the parameter space, into an area that you just sort of got stuck, and it got worse and worse. That was bad. Again, this is sort of AI story time where I'm just making up tales and hand waving, because it's really hard to prove these things.
But this is interesting. Like the values would look normal, but the combination of weights would create like weird loss behavior. Like it's okay. That's very counterintuitive to me, but okay, that makes sense.
And I've seen other things. Like maybe it's rat holing too much, but this would happen to batch norm, and there are a few papers out there who incorrectly identified that. So when you push sort of the bit counts down, sometimes things will start exploding, or Mantissa bit counts down. And there were a couple of papers out there, not from NVIDIA, from other places, that were alleging that it was somehow overfitting, because what you would see, that training curve looked okay, but the validation curve would explode at some point. So people surmised that it was maybe overfitting, but it wasn't really that. But what was happening is that all the histograms generally looked okay. If you looked at things like L2 norms, maybe your gradient norm started increasing, right? And then roughly what was happening, and there's actually a paper of that from FAIR from earlier this year, like why gradient magnitudes would increase throughout training if you have enough data. But then your weights would start evolving, and then things like batch norm accumulated statistics, which are used for evaluations or inference, they could not keep up because they had sort of exponential moving average, but values underneath would move faster than those statistics would change. And that's why your sort of evaluations would collapse. But again, it was sort of like a weird effect that if you started, having too few bits in gradients, that would accelerate the change in gradient norms, and that would have an effect on weights and thus activations, and then just sort of that's how you would end up with batch norm parameters getting outdated. So there are sort of like these weird indirect interactions that actually take quite a while to take effect, which makes debugging extra exciting. All right. So this is just a quick graph because it's kind of interesting to look at. This is what happened to scale factors, right? So scale factors were dynamic. And the way we did that was basic, because you don't really know what scale factor to choose, right? What best scale factor for one network is not necessarily a good scale factor for another. So we just made it dynamic because, again, this scale factor application was very, very cheap. The only thing you do is take the loss, which is a scale factor, a scalar after the forward pass, multiply that with something, and then backprop is just like it would have been otherwise. Nothing else changes. So there's really no extra cost. But if you don't have the right scale factor, then maybe you're, fleshing too many values to 0 and bad things happen. So the idea was find a scale factor that's as large as possible. So we'd really start out with a maximum scale factor, and that would guarantee that something overflows and generates those infinities and nans. But those we can actually detect in the optimizer. So as soon as we saw infinities or nans in the optimizer, we would just skip an update and then decrease the scale factor by a factor of 2. So that's what you see here. At the beginning, we choose a high scale factor, we overflow, so that gets dropped. Then it works for a while, overflow happens, it gets dropped, works for a little bit, overflows, gets dropped. And then here it works quite well for a while. And the heuristic was that every 1,000 steps, if we did not have to reduce the scale factor, then we would increase it by 2, right? So basically, kind of push it, So if you haven't run into problems for a while, make it larger. And if there's no problem, make it larger again after a while. So that's what you see here. We made it larger. It was fine for 1,000 steps. We made it larger, fine for 1,000 steps. We increased it, ran into a problem, backed off. And after 1,000 steps, we tried again. But you can see the scale factors kind of stayed in this range. So the smallest scaling factor was 2 to the 20th, which suggests that, well, actually not suggests, it indicates that the maximum weight gain in magnitude never exceeded 2 to the -5. Right? So that's where those representations that go into magnitudes greater than 1 were really unused, right, in those floating point formats. Okay, maybe I'll skip this for interest of time, but this was an experiment to sort of determine, okay, how bad is it to skip updates? So this was just Resonant 50 training, and orange is a default training, and blue was if we skip 0.1% of updates, just to see if that affects accuracy, and it didn't. And the reason you see regions here, because there's quite a bit of run-to-run variation. So for each one, we actually ran multiple training experiments. So back then, Resonant 50 was expensive, so you can sort of see there's, I think it was maybe 10 experiments, 10 runs for each. Today that'd be even more prohibitive with large LLMs. Okay, so that was 16-bit training, but basically has long replaced FP32, and then BF16 really superseded FP16 because its wider dynamic range made implementation simpler. Right? No need for scale factors, don't have to keep track of them. Also, I should point out that in FP16, this loss scaling only applies to gradients. And if for whatever reason your activations do hit high magnitudes or weights, then you'll overflow. And that's going to be a problem because you can't really apply cheaply scale factors to the forward pass. Eventually we ran into that with smaller types, but then for 16-bit types, you could just use bfloat 16. Now, occasionally cases come up where BF16 does not have enough mantissa bits, so some operations fall back to FP32. Or if you have FP16, you can do FP16 there. Right? There's some evidence, for example, that when you're dealing with long sequences and attention-based networks, then for attention softmax inputs and even the outputs, you want more precision or more mantissa, right? So FP16 can work there, where bfloat 16 sometimes fails. So, and again, illustration that we've seen earlier, like dynamic range versus precision for the two. Okay, so 8-bit. So 16 is nice, but 8-bit is nicer because it's smaller, so you could make it faster. 2 encodings, E4, M3, E5, M2. We've seen this graph before. This one does have several variants, right? So there's OCP, which is sort of Open Compute Project, which is a standard specification body, and that's where a number of vendors like NVIDIA, AMD, Google, Intel, and ARM got together and came up with a spec for how to encode those bits for FP8. GraphCore have a different implementation in their hardware. Tesla, for their training chip, also have a white paper describing their implementation. It's really more of a block format in their case. And as I mentioned, there's an IEEE working group that has been working for years and is still working to standardize something. And it appears that they're sort of moving in a direction to be different from all those other ones. But we'll see how much that matters since the world is trying to go below 8-bit by now. And the differences come there from various choices. So for example, OCP format largely follows IEEE, even though E4 M3 gives up, I think, NANds to have a bit more encodings. But so OCP does have plus and negative zeros. And I think IEEE working group, the draft that they had a few months ago did not have a -0, and they were recovering that bit. I want to say, but I'm less positive. So I'll say it, but I might be wrong here. I think GraphCore also may not have -0. They save it for some other encoding. Also, exponent bias choice. So OCP formats follow a IEEE approach on choosing the exponent bias, just based on the bit count. Others were proposing changing the bias to something else. I would argue in practice that really doesn't matter because FP8 certainly needs scale factors per tensor or even finer granularity. So at that point, exponent bias really doesn't matter because you have a separate scale factor anyway. So that's what kind of have this comment that a lot of these differences are more philosophical than have a real impact on AI workloads. And that's part of the reason why OCP group just got together and said, okay, let's just have a spec so we have something to write software for. But yeah, over time, we'll see what gets adopted mostly. Okay, so a little bit on FP8. So it has a very narrow dynamic range, and that definitely it's insufficient to store all the tensors with a single scale factor. So you can't just pick it. So dynamic range for your 5M2, it's about 18 powers of 2 binades. For your 4M3, did I mess it up? Oh yeah, it's in reverse. I'll correct the slides afterwards. Yeah, I messed this up. So it's 18 binades for your 4M3, 32 binades for your 5M2. But they're insufficient to have a single scale factor for all the tensors. So for, let's say, activations and activation gradients and so forth. And there's a quick illustration of that here. This, again, same kind of type of histogram, but just for different operations that produce those values. So there's projection, so that's linear layer right after attention. There's up projection, down projection in FFN, QKV projection, and one of the batch matrix multipliers inside the attention. And so you can just sort of see that they have quite different dynamic range needs. Like in purple, this actually has quite a wide dynamic range that it needs, right? And also, let's say green and yellow appear over here, but then the rest of the colors are over here. So even though if your data type could cover the dynamic range needed by one of these tensor groups, it's not sufficient once you look at the union of all kinds of tensor groups. And even for the same tensor type, I think the graph below here, I forget for which layer. Most likely it's up projection in the FFN. But I think green and blue are just sort of in different positions in the network. So one is closer to the input layer and one is closer to the output of the neural network. And again, we just sort of graphed the histogram of the values that occur during training. And per tensor, there's roughly maybe the same dynamic range, but if you look at their union, it's pretty wide and starts exceeding what either one of these data types could cover. So that's where you end up having scale factors now per tensor or even finer granularity, right? So per tensor scale factors work for some networks. So for a bunch of Megatrons at NVIDIA, they work just fine. But then as data sets grew, we had to go away from static scale factors to dynamic. I can get into that if people have questions, but that gets involved. And then per subtensor was needed by some networks as well. So like namely DeepSeek, for example, right? They had block and sort of sub-row scaling that they implemented. So per row scaling is actually cheaper computationally, but per block gets pretty expensive before Blackwell and MI300, so before the MX formats.
So per row seems a bit counterintuitive to me because it's the same scaling factor for a whole bunch of features. Like I would imagine that, like, yeah. So is this just how come per column doesn't even show up here?
So basically, when I say row and column, so myself always get confused by those, what's logically row and column. But really, when I say row here, it's really along the dot product dimension. That's what matters.
Oh, I see. It's the inner dimension. I see.
Yeah, because the idea, and I think I can jump to, oh yeah, I do have it. Okay, let me just jump to this slide.
Yes.
That'll explain the cost, at least computationally, right? So the top graph here is what I would have, what I call per row scaling, but it's really for one tensor is per row, for the other one is per column. So in green are the values in let's say a vector, and in purple is a scale factor associated because it's already kind of a quantized type. So if you're computing a dot product, again, going back to that linear equation we had earlier, if all of these values share one scale factor and all of these values share another scale factor, then we compute the dot product in low precision, with cheaper math, get the sort of black element as an output, and then apply those scale factors in higher precision. So that's what I would call, quote unquote, cheap. If I make my sort of segments smaller, so now each one of these sort of segments in the bottom graph has its own scale factor, even though they're the same color here, then I can no longer compute this entire dot product in some lower precision and then apply scale factors. I have to do, one segment's dot product, apply the scale factors. Next segment dot product, apply scale factors. Only after that, I can add those two segments contribution to the dot product. So now I'm adding this overhead. And if there's no hardware support for that directly, then you have to do extra math in addition to your, matrix units. And you have to do it, many times during the dot product. So it will slow down your dot product potentially. So that's where, the coarser granularity you have for the scale factor, the cheaper it is computationally. And even if you have hardware support, it's still, some power cost will happen there because of that. But the key is that you want your scale factors to be applied along the dot product dimension. That way you can feed your matrix unit, whether it's NVIDIA Tensor cores or, I don't know, TPU systolic array or AMD's implementation of a matrix unit. They all need to do that math within the matrix unit in some quote unquote cheap precision, and only apply scale factors after that. I don't know, does that help answer your question? Or
It did, yes.
okay. Let me see, did I leave here? No. Okay, so yeah, I guess I just talked about that. But then for result quality, intuitively having smaller blocks is better, right? Because if your block gets smaller and smaller, then potentially need a narrow dynamic range within the block. Or another way to think about it, that your outlier magnitudes, large values, go into a smaller block, so their blast radius is smaller, right? They can only flush to zero values within the unit that they're being quantized in. So if your quantization unit is entire tensor, in the worst case, you could have such a large magnitude that if you represent it just flushes all the other values to zeros because they're so much smaller than it. But if you have a smaller block, let's say block size 32 as in MX formats, then that large magnitude can only sort of, blast the other 31 values in the same block as it, and it doesn't affect other blocks because those guys will have their own scale factors. So that's sort of the intuitive explanation why smaller blocks are generally better or should be better for accuracy or quality of the neural network, but they're not great for speed unless you add specific hardware for that.
What about like mixed? So there's a question from chat from Donyon, which is what about like mixed scaling formats? Like why not have one tensor in per tensor scaling and one tensor in per block scaling?
So you can have that. It all depends on what kind of hardware support there is. So as soon as you have block scaling for one of the tensors, you need hardware support in the matrix unit for that. Because if you don't have hardware support in the matrix unit for that, then effectively you'll have to, so if we just look at this picture and I just wipe out all the purple sort of squares down the column here, right? So those just have the same scale factor. But it's still the case that I cannot compute the dot product of the first segment and add it to the dot product sort of contribution from the second segment without applying the scale factors first, right? Because they're sort of in different regions once they've been mapped. So as soon as one of the dot product vectors has block scaling, if you don't have hardware support for that, you'll have to do extra instructions for that.
That makes sense. Okay.
Yeah. Cool. All right. So I think this sort of transition is to OCP MX formats, right? So for FP8, as I said, recipes evolved. It started with per tensor scale factors, and then originally was just sort of heuristic-based scale factor selection, right? So that's one aspect. When, let's say, some operation produces a tensor, it produces it in high precision, those values set in registers. You want to write low precision to memory. But before you can encode them into some low precision type, you need to know your scale factor. And if you don't know that scale factor, you have to look at the tensor values. Well, oftentimes what you'll have to do, you'll have to write out that tensor to memory in high precision. Then you know what the maximum magnitude was. Then you have to go through it again and then do the conversion. Right? So that adds extra memory trips. So it's costly. So the heuristic originally was that we just used that tensor's past history. So we said, okay, well, in the previous iteration, this tensor's largest magnitude was X. So we'll assume that we'll choose the scaling factor based on that previous history. And really, we would maintain, let's say, like a moving window of scale factors over some number of steps, and then pick the largest one out of those and make that the scale factor. And like I said, that worked great for a couple of years. And then training started stalling once data sets shifted significantly. So then shift happened to the dynamic scaling, and then folks also went to finer granularity with FP8, which added overhead because there was no hardware support for that. And then starting with Blackwell and AMD's 300 series, there's support for MX formats, which really are just a definition for a fine-grained block format. Right? So the idea is your data is 32-element blocks, and they could be encoded in FP8, FP6, or FP4, as far as elements are concerned. And then you also have metadata that's associated with that block, and that's an E8M0 scale factor, basically just powers of 2. And that's just a quick illustration how to decode that, right? So you have your data in yellow stored, metadata, some power of 2, so let's say 16. So really each value is the product of the metadata and that value. So 1.5 turns into 24, 0.5 turns into 8, and so on. But now, like I said, granularity is fine. It's 32-element blocks, and hardware has support for that. So technically, there's no loss in speed when you do math now on these vectors. But you do need newer hardware for that. Quick illustration of MX FP8. So that's a slide just ripped out of my GTC presentation earlier this year. So for inference, MX FP8 is kind of interesting because unlike Int8 and even sort of vanilla FP8, you don't need QAT. You don't even need to do PTQ. So you don't need to do any kind of calibration. Literally all of that happened here. We took a network trained in higher precision, except for DeepSeek, which was trained in FP8. But with different scaling factors. And then we just converted to MX FP8 without any scale factors from calibration. So it's just sort of straightforward cast-only operation. And in the figure here, you can see accuracy. So baseline was whatever precision the model was trained in. So bflow 16 for everything other than DeepSeek R1. And in orange is what happens when you run that same network. So same weights, but just cast to MX FP8 when you load up the model, and all activations were just being cast to MX FP8 at runtime. And accuracies are basically indistinguishable. So I think it's a pretty nice story for inference of high precision trained models without really any extra headache when quantizing them to a smaller type. And again, the big reason for that is the small blocks and each having a scale factor. Training, MX FP8 also makes it easier. So for FP8, there were all kinds of recipes, but for MX FP8, because blocks are smaller, we're able to keep more more tensors in FP8. And we ended up using only E4M3. So we dropped E5M2. So E5M2 has a wider dynamic range, which we found in vanilla recipes when your scale factors were sort of at a coarser granularity. We needed E5M2's wider dynamic range to make training work. But also some tensors needed 3 bits of mantissa precision. So those tensors were just left in high precision if they needed both dynamic range and higher precision, because FP8 could not do. But with MX FP8 formats now, since we can have scale factors at fine granularity, they sort of take care of the cases that needed wider dynamic range and mantissas. So again, that makes training much simpler. And again, just some training curves here, green and black. So black is bflow 16 baseline, MX FP8 is in green. They just match up. And then the bottom here is just evaluation graphs, right? So different evaluation benchmarks shown in both BF16, vanilla FP8 and MX FP8. And the MX FP8 in green, just matches black. Whereas orange one sometimes, because of the coarser scale factors, loses a little bit. So you would have to do some PTQ or QAT. All right, that gets us to FP4, which is the smallest data type so far. So OCP MX FP8 spec defines the encoding. It's easy because I just listed all the magnitudes you can represent. There's also negative versions of these, right? So you can only represent 0, 1/2, 1, 2, 3, 4, and 6. That's it. That's how it samples the real number line. It departs from sort of IEEE, like in the sense that it has no encoding for infinities. It has no encoding for nans. We kind of rely on the block exponent or block scale factor to indicate that the entire block is nans or entire block is infinities, simply because even with all of these sort of recycling of the bits, still we can only represent just these magnitudes. So if we had to represent infinities and nans, this would have dropped substantially from, we could sample many fewer points on a real number line. Again, slide ripped out of GTC just shows what happens with FP4 inference if you only do post-training calibration, no further training, right? So we'll see it. So that's blue is the baseline, sometimes FP8, sometimes BF16. Orange is FP4, but without any kind of fine-tuning to recover accuracy during quantization. So we see that we do lose, a percentage point or a couple of percentage points of accuracy across various networks here. It's not catastrophic, but it's certainly, lower. So max calibration was used in this case, and you can see, all the details in the slides after. But so to recover that accuracy, you have to do some kind of training with quantization in the loop, right? So you have to do quantization aware training. There are some other techniques we can sort of distill, but I sort of grabbed a few networks. So a couple of nematrons, and the green is what happens with QAT, so quantization aware training. So you can see it goes from orange to green. We recover accuracy. Large nematron was actually okay, even with just PTQ. And then this is Llama 3.1 that we grabbed, a couple of years ago. And without any kind of training, we got accuracy in orange for FP4. But if we did a little bit of distillation-based training for Llama 3.1 on 8B, then we got to the green accuracy. The catch with QAT approaches is that we've discovered, and I think others have discovered the same thing, if you're doing any kind of quantization aware fine-tuning to get the model adjusted for lower precision, you really have to do that with the same data that the model was pre-trained or even fine-tuned on in higher precision, because you can get to situations where you have very different data set on which you train. That data set might work for your networks, but some other network was trained on a different data set. So if you're continuing just the training of another network with a different data set, your loss will keep improving, but your downstream task accuracy really takes a hit, because I guess it's just seeing a different distributions of data. So that's one sort of challenge with QAT.
It's a tough flaw because it means basically only the lab that produced the model can give you like a quantized version of it. That's
that's a bit unfortunate. That's
yeah.
where there's some. That's why for the Llama, the traditional QAT was not working well for us. And it's actually not a problem related to quantization. That's a problem for continued training in general, irrespective of precision. But that's where we just basically did some distillation, right? So the idea is you just put whatever data through the unquantized network and quantized network, and then your loss for fine-tuning is just simply the difference between the two tensors in a quantized and unquantized version. So you're not really training for a particular task metric. You're just training to minimize the difference between quantized and unquantized.
I have a few more questions on this slide. So let's see. There must be some. Oh, yes. Okay. So the first question is, like, for example, like NVFP4 is like one example of like deviating from like I think the MX spec didn't even come out all that long ago. And if I recall, NVFP4, we have a NVFP4 competition actually ongoing right now on the server where people are competing to write like the fastest NVFP4 kernels. But like one, it uses like different like scaling factors, like smaller block sizes.
Yep.
How does this happen? Basically, the spec writers get it wrong. Like, could you sort of help us understand of like why NVIDIA felt like yet another D-type would be more beneficial for researchers here?
Oh, sure. Let me see. I have that here. So it's actually a good segue. So I can comment on how that happened, since I was involved in both OCP spec and NVFP4.
Oh, excellent. Okay.
So a lot of these things take quite a bit of time to come up with, right? And then oftentimes specs end up being some sort of compromise, right? So work has been going on at NVIDIA on this for quite a while. And then the spec effort started. So the spec sort of settled on one implementation, right? So that's a good, this slide maybe on the very left explains the differences, right? So MX FP4, which is an OCP defined specification, it has 32 element blocks and scale factors are 8 and 0, right? So just powers of 2, because 0 mantissa bits. NVFP4 is sort of, we can see it as a bet by a vendor that it's something better, right? And that had been in the works for a while, or various things that evolved into it had been in the works for a while. If you look at some publications from NVIDIA research, they had sort of fixed point based formats that worked for some cases, not quite for others, and that's where transitioning those to floating points sort of ended up in this. I forget what the original format was called in their paper, but maybe it'll come back to me. Anyway, so there were efforts going on for a while, and then spec sort of settled on one compromise, and then at NVIDIA we felt that there may be benefit to this different variant of FP4, so we put that in hardware and we shipped that as well. So they're both available in Blackwell, right? So people can choose whatever they wish to use, or can experiment with both. And I guess over the next slides I'll show some cases that might give advantage to NVFP4, but it's early-ish to tell. So on this slide, there's 2 training sessions, and there's a paper. I didn't include the link. I'll add it to the slide. There's a paper from NVIDIA that came out on FP4 pre-training maybe a couple of months ago by now. It's an archive. If you just Google NVFP4 pre-training, you'll find it. But it sort of did an ablation study where, I guess x-axis here is just tokens and trillions that, network is trained on. And then the y-axis here is actually not the loss, but it's relative difference from bfloat 16 training session. So lower difference is better, but lower difference would be up, right? So the zero difference is at the top. So if you just had a curve that was just flat here along the top edge, that'd be the best case. So in both of these cases, FP4 training sessions were lagging behind bfloat 16, but green was lagging by less than red, right? So the red is further away from the top edge. And yeah, so red is MX FP4, green is NV FP4. Another interesting way to look at that is, well, what does that mean to your training session? It doesn't mean that you cannot use MXFP4 training at all. It just means that maybe you have to train longer, right? And that's what was done here. So the X on the right graph, X-axis is tokens in trillions used for training. And Y-axis now is the validation loss, sort of in absolute terms. And the sort of the line through here is where NVFP4 training session loss was after 1 trillion tokens. And MXFP4 was, above it. Right? The Y-axis doesn't go all the way down to 0, right? So it's, this gap is here for illustration. But then if you continue to train in MXFP4, loss would keep decreasing, right? So, and we see that that loss intercepts the same level as NVFP4 achieved loss after 1.36 trillion tokens. So one way to interpret that, you can train in MXFP4, that's what this experiment shows, but you might have to train, 36% tokens more to get to the same loss value as NVFP4 did. And then, so you can sort of think about, okay, what does that mean to the cost of training? So that's one aspect, and maybe I'll pause to see if there are any questions.
So is this like one of those things like where, again, we need hardware units for both, though? Like, or is it just you just bet on NVFP4 and then just like, and then do some sort of simulated thing for MXFP4? So
again, I hesitate to speak on NVIDIA's behalf since I'm no longer there, but I'll pretend that I'm speaking, I don't know, half a year ago. So from NVIDIA's point of view, NVIDIA support, was part of the OCP spec for both FP8 and MX formats, right? And it was, one of key members. So NVIDIA shipping hardware for that supports the spec format because that's good for the community. And then there's also, the thinking, okay, there's a format that's not in the spec, at least not yet, but it might have advantages. So NVIDIA's choice was to ship it. So in, Blackwell case, both of these formats are natively supported in hardware. In other cases, if somebody's making hardware from scratch, then they kind of have to make a decision, what could they ship? They can choose to ship both, or they can ship one. And the way to interpret this graph on the right, so let's say I'm making hardware and I'm trying to decide what to ship. And it really sort of depends. So let's say, and again, this is one sort of experiment that provided these numbers, but let's say it's very generalizable. Well, if I could implement MXFP4 hardware, let's say more than 30% cheaper than NVFP4 hardware, I might come out well, or at least break even in that cost. So let's say I implement somehow, for whatever reason, let's say MXFP4 training for me is twice as fast per step than NVFP4. Then even though I have to do 36 more steps, I still come out ahead at the end of the day because each step is at half the elapsed time. Now, in these two types cases, I don't think it's the case, but that's how you can sort of make trade-offs between some data types. So like one data type maybe is better convergence-wise than a number of steps, but if the other data type can get the same accuracy in more steps, then you just sort of raise the threshold that it has to cross in terms of speed. But it's still a viable choice potentially, right? And I think more and more the world will probably have to think about things in this way, because as you go to fewer and fewer bits, I think it's going to be much and much harder and at some point impossible to maintain the same sort of convergence behavior as higher precisions. But then you're just looking to trade that off for, however much you're giving up in convergence speed, you need to more than make up for that in the actual speed per step, and then you still come out ahead. If that makes sense.
It does, yes. So Vipul is asking, I think, a related question, which is, if he recalls correctly, NVFP4 does multiple levels and granularities of scaling. It has a global scaling, then a block level. What's your thoughts on such schemes where scaling is almost like fractional block size?
Yeah, so NVFP4 needs that because if we look at the scale factor, so it is nice to have those mantissa bits, and I have a couple of slides on that, so we'll walk through that. But again, it's, scale factor is 8 bits. And it's 8 bits because it's just sort of a nicer addressable unit in memory, right? And the scale factors are stored separately from the values themselves. You can address 1 byte, so it makes things kind of simple to fetch. So, and we did a study, how many manticipits to use, and sort of 3 was sort of a best trade-off there. Because if you go higher than 3, then you really have to give up a lot of exponent. But yeah, exponent is only E4. So now when you store the scale factors themselves, well, they have to have a scale factor of their own. And so far that's been per tensor. So you don't flash like the tiny ones to 0. So that's, I think, why you need, not always, but there certainly are cases where you need 2 level scale factors, 1 per block and then 1 per tensor just for the scale factors themselves. It's really just sort of almost a necessity to reduce the average cost in bits per value, right? Because we could have said, well, just store more bits here. Let's pretend that 8-bit addressing is not what we need. Let's say we could have stored E8 M3, and that's easy to store and address in memory. Well, then your average size per bit actually goes up quite a bit, right? Because let's say you have 16 4-bit values, so that's 64 bits already. And then if it's E8 M3, that's 11 additional bits. So now you have 75 bits in total per block, and you divide by the block size by 16, you end up with some average size per bit. So you do want to keep this small as much as possible. And 2-level scale factor, or fractional scaling, if you want to think of it that way, it sort of helps amortize those extra bits. So now what you have is still just 8 bits of scaling per block. So total bits per block is 8. And in addition to that, you have, I think NVIDIA, they just use a 32-bit float for the per tensor scale. So you have an additional 32 bits. But those 30 additional bits are amortized over the entire tensor, right? So they're pretty, quote unquote, cheap at that point. So yeah, so this multi-level scaling is just a way to end up with a smaller number of average bits per value, because you amortize them over sort of larger scales. Or blocks, levels, I guess.
Makes sense. Yeah, let's keep going.
Cool. All right, so a little bit on scale factors, right? So that will explain some intuition why you might want to have precision or extra precision in the scale factors, right? And again, scale factor recipes can vary and probably will evolve. One thing I should mention here, maybe I should have put in the slide. So if you look at OCP MX FP spec, you can just find it by Googling OCP MX FP. It actually has a bug in the suggested specification for conversion to the low precision formats, and we're in the process of correcting that. So don't follow what's in the spec, and let's say follow what's in NVIDIA's paper, and I think there's some other papers that people publish. So there can be different ways to choose scaling factors that work. But the classical recipe is basically find the maximum magnitude in your block in some high precision, then compute the encode scale factor to take that maximum and map it as close as possible to the destination format's maximum without overflowing. And we don't want to overflow because in some FP8 training sessions, we saw if we overflowed the destination format and then just saturated the value after scaling to that. So a bunch of high magnitude values just started becoming indistinguishable because they would just all get converted to, let's say in FP4's case, they would all just become 6 and you cannot tell them apart. That was stalling training to some degree, and that was actually in FP8. So that's how we followed this recipe. But so now the question is, if you follow this classical recipe, how much does scale factor precision matter, right? Or scale factor format itself. And that's where the mantissa bits of more precision can potentially expose more of the format's dynamic range and can actually more accurately represent the block values. So a quick example of that, let me see how we're doing on time. Okay, I'm close to the end here almost. So if we look at FP4, it's easy to look at because it only has these values that it can represent, or magnitudes. And let's say we have a block of high precision values where the largest magnitude happens to be 3.6. So let's just pretend everything is positive for simplicity, but no loss of generality. All right, so we have 3.6. Well, that cannot be represented exactly here, right? Because there's nothing that would get around it either to 3 or to 4. But we have to find a scale factor. And again, we're looking for a scale factor where the goal is to take 3.6 and map it to 6. And then all the smaller magnitudes would also get increased and map somewhere in this range. So if our scale factor is only 8M0, meaning it can only be a power of 2, it will have to be 1. Because if I pick my next available scale factor, which would be 2, because that's the next power of 2, it's too large because 2 times 3.6 is 7.2. That already overflows 6. And let's say I decided that's bad. I don't want to do that. So I have to pick a smaller scale factor than 2. My only choice is 1. Well, that's fine. So 3.6 gets multiplied with 1, and it gets rounded to one of the values here. It'll get rounded to 4 because 4 is closest to 3.6. So what we end up doing is that we will not end up using the sample 6 in the FP4 format at all, because the largest magnitude I had just got converted to 4. So nothing else in that block will get converted into 6. They can only be smaller. So I just wasted sample 6 out of FP4, which is about 15% of the samples that I have, because I only have 6 of them to begin with. So that's one potential sadness. And then if we look at what E4M3 would do, well, E4M3 can represent 1.625 as a scale factor, and 1.625 times 3.6, I think is like 5.85 or something like that, right? So that will round to 6. So now I'm no longer wasting the 6 sample. So I just saved myself. And that's how I end up using more of the dynamic range of FP4 than possible with just powers of 2. So that's one potential, goodness. And the other one is now 3.6 gets more accurately represented when we decode it, right? So if I look at what happens with E4M3 scale factor, I took my 3.6 original value, I multiply with 1.65 scale factor, and I round to 6. If I decode, I have to divide by the scale factor, right? So 6 divided by 1.65, I get back 3.7 roughly, right? That's what I get back. So it's not exactly 3.6, it's off. And we can see, the error is about, 0.1. If my scale factor was only 8M0, then I took 3.6, multiplied with 1, rounded it up to 4. Then that 4 comes here. Now I have to decode. I have to divide by the scale factor, which was 1. So I still get back 4. So now the error after encoding and decoding is larger. Instead of 3.6, I'm getting 4. Whereas before, instead of 3.6, I was getting back 3.7. So those are the two potential, benefits of the scale factor having precision. It sort of enables more of the dynamic range for your block in some cases, and it also can more accurately represent the largest magnitudes. How much that matters, it's probably a bit early to tell, right? More training sessions will have to happen. This is still, bleeding edge work, but that was sort of the reasoning why we saw in FP4 having, potential benefits. Also for PTQ quantization, which was losing accuracy, but having more mantis bits on a scale factor was helping us keep more of the accuracy than just powers of 2. So that's why I guess we felt compelled to also ship in FP4 and see how things shake out. So maybe that sort of adds to the answer to your earlier question, Mark. Okay, other works, I'll skip through this in the interest of time. So, people have been publishing on binary, and I would call it ternary training. They call it 1.58-bit training. So, one paper from early last year was pretty interesting. That's basically just using -1, 0, and 1 values to train, of course, with scale factors. And they have to change quite a few other hyperparameters to make it work, add more normalizations and so on, but it's certainly interesting. Code books, I mentioned earlier, and that's how you sort of get to maybe even sub 1 bit per value. General idea is have lookup tables as a compression technique, right? So if you have 16 entry table, you have 4-bit indices, but I could have, data types that are much larger. In the table itself could be FP8, I don't know, FP11, whatever. And again, for DNN use, so lookup tables are nothing new. They've been around for decades. For DNN use, dates back to at least 2015 when Sung Han published a paper on that. There might have been some work prior to that that I'm not aware of. So just some directions. So I think, and there's also techniques to adjust neural network tensors to be more amenable to low precision, right? And again, active area of research. General idea is you have a tensor, and you'll apply some transformations to that tensor to reduce the dynamic, usually to reduce the dynamic range required for the values, right? So examples of those would be additional normalizations, and that's what sort of ternary training does. It adds more normalization layers, after each gem, for example. Sometimes that helps, sometimes that actually hurts, so, when we've done some experiments. And there's techniques like AWQ, smooth quant, SVD quant, random Hadamard transforms, and so on. So all the ideas here, you do some extra processing on the tensor that you can easily undo, that somehow makes tensor sort of more behaved for low precision quantization. And like I mentioned, usually they try to address the dynamic range. Any questions before we move on to FP floating point quirks?
No, I think we should keep going.
Okay. All right. So I just have a couple of slides here. So kind of going back to, again, floating point specifics here, and some quirks that do come up, and you see them sort of brought up more and more online in the AI context, but really those things have been around for as long as floating point encodings have been around, right? So some things are like non-associativity of additions, and then fuse, multiply, add, right? So both of those things sometimes can be surprising to folks, but they're sort of discovering the old quirks. And in all of these cases, maybe I won't say all of them, but in vast majority of these cases, rounding is really the reason behind these quirks. So floating point non-associativity, the key observation is that even though in sort of real number algebra, order of additions does not matter. So A plus B plus C is the same as B plus C plus A. In floating point, it is not. And that's because you have finite number of bits and finite precision. And it's the rounding of intermediate values that's causing the differences. And we have an illustration that we'll glance at in a sec. So things that can change the order of these operations, right? So if every time you did A plus B plus C, your results would be purely deterministic, right? So you see these things come up in the deterministic training or even deterministic inference discussions. So if you change hardware, you will get different dot product instruction sizes, and that can actually will not change the order of operation. Actually, it does change the order of operations when you really think about the summation, right? If you compute a dot product of 1024 elements, if you do it, let's say 32 elements at a time or 16 elements at a time, you just change the order of additions. But even on the same hardware, you can get different orders of operations, either because of different compiler optimizations, right? So different compiler flags, or if you're using atomics for things like reductions, because then that's really sort of like runtime scheduled effectively. And related to that would be like work queue-based implementations, right? To where different, let's say, threads grab work from a work queue, and because of thread scheduling now, some thread might grab different chunks of work that it works on. And again, that can change addition order. And usually there'll be deterministic versions of kernels to avoid that, but these are some of the reasons that can cause it. To understand why that's happening, I sort of figure, okay, I can start with floating point swamping. So that's a special case. It's really just when you add two values, and what's happening is that the values magnitudes are so different that the sum will be just a larger magnitude if they're positive, right? So quick example with E5M2, because it's fewer bits to show. Maybe I will not like nitpick everything. Folks can look at it afterwards. But let's say we're adding numbers 32 and 3.5 in E5M2 representation, and the output will be 32. Right, which is algebraically incorrect, but that's the best you can get if your inputs and outputs are always E5M2. And the reason for that being is that I convert them to binary formats. So you can see one is 100, one is 111. They have different exponent values because they're different magnitude values. So we have to do binary point alignment. It's just like if you were adding values in decimal system. So you have to make exponents the same, but to make exponents the same, you have to make the exponent larger for the smaller value. And because of that, you right shift the 1 bits by shifting in zeros. So these are still the same values that you're adding. Once you add them, you get this result. And the key is that the result, to be represented accurately, needs all 6 bits of the mantissa. But now you have to convert back to E5M2, which only has 2 bits of mantissa. So all the bits in red here are going to get victimized by rounding, right? And that's what happens in any of these representations. If the value cannot be represented accurately in the destination format, rounding will happen. And in this case, you round to the nearest value, and the nearest value will be 100, right? And so that's how you get 32 as an output. So that's just swamping, how that occurs. And then just building on that, maybe I'll skip through this in the interest of time. But now, let's say we're adding values 32, 3.5, and 4. And based on the order in which you add, you will get a different result. So if you first add 32 and 3.5 and then 4, you will get only 32. And maybe that's quick to describe, right? We just saw that 32 and 3.5, because of magnitude difference, will just produce 32. And after that, I'll have 32 plus 4. And same kind of problem will still occur. I will lose that 1 bit after rounding to nearest even, and I still just get back 32. So it's as if we didn't do any additions at all. Here, if I first add 3.5 and 4, I will get 8, right? So it's not 7.5 because that could not be represented because of rounding, but I get 8. And then I add 32 and 8, and we will get 40 at the end. So just quick illustration, if you want to sort of go through the bits, you can. And it doesn't have to be like a swamping case. There will be other cases, but the principle is exactly the same. Intermediate values that you get change magnitude based on the order, and therefore they incur different rounding sequences, and that's why you will get different results. And it's just unavoidable in any kind of floating point representation, simply because, like as we said earlier, the number of real values is infinite, but any kind of number implementation in hardware has finite number of bits, and because of that, you will have to round. And as soon as you round, your sort of traditional algebra laws start breaking down, especially when it comes to associativity. Fuse, multiply, add, that's the last thing before we wrap up. So it's a Quirk, so like a subsequent IEEE version of 754 introduced fuse, multiply, add operation, right? So what it does, in a single instruction, it can multiply A with B and add C all at once, or at least conceptually. A single instruction does that, and it's only for scalars. So it's, as I mentioned, defined by IEEE. It's implemented in most modern CPUs and GPUs. All the main ones have it. And one requirement of IEEE is that the product A times B, before the addition happens, must not lose any precision, right? So you have to maintain it in full precision without losing any bits. And that's a key difference that can cause some interesting quirks later on. So in vast majority of cases, fuse, multiply, add is more accurate than a sequence of first floating point multiply, round to the destination format, and then add. But it can lead to surprising results. So again, this is an example that comes from Khan, basically the author of IEEE 754. So one case is where if you have x times x minus y times y, may not be 0 even if x is equal to y, right? So technically, it's really same value squared subtracted from the same value squared. So that's kind of surprising algebraically at first, but if we dig into what's happening underneath, it's understandable why you could get non-zero outputs in this case. And you will get this inequality here whenever x times x product requires more bits to be represented accurate or precisely than your destination format has, right? And the reason for that is if you do fuse multiply implementation, it's really logically what happens is first, let's say you compute the y times y product and you store it in a temp variable. It will get rounded because you're storing into a destination variable. And then only after that you call fuse multiply add, and then you'll provide x and x, and you subtract the temporary value you just computed, right? Because fuse multiply add cannot take 4 arguments, it can take 3. So that's why you have to pre-multiply one of them and then submit as an argument. So, but now in this case, x times x does not get rounded at all, right? Because IEEE standard requires that this product must be maintained in full precision, and then you do the addition. So x times x didn't get rounded, this temp value did get rounded, and now you subtract rounded value from unrounded value. So if you lost bits during the rounding, now you can actually get a non-zero answer. Whereas if you do fmul and fadd sequence, then fmul of y happens and you get rounding, then fmul of x happens and you get rounding, and then you do addition. And in that case, you will get a 0 every time. So it's a quirk. Which one's the right thing? It's hard to say, right? Because it's unavoidable with finite representations. And so these effects usually will manifest themselves through compiler optimizations. You know, how compiler decides to look at your source code and generate fuse multiply adds, or just multiply and add sequences. Usually compilers have flags to disable diffusion if you want that, or even you can have intrinsics per operation type, but something to keep in mind. These things can happen. I want to say, yep, I think that's the last slide I had.
Sweet.
So
Thank you, Paulius.
I'll stop here and see. Yeah.
Thank you. Yeah, this is like a tour of the force, so thank you. So I think there's a lot of questions in chat, and then I have a lot of questions as well. So let's just go over them, and when you get tired, just let us know.
Let's go.
Okay. So Vipul is asking, can we expect an OCP schema for Tensor Core's FMA ops because it's lacking in the IEEE standards?
Well, that'd be a question for hardware folks, which I no longer represent. I don't know. I would say that, personally, I guess maybe a need would be demonstrated for that. Because I guess today on all the hardware that I'm aware of from either NVIDIA or AMD, what's going to happen is that the OCP formats are only supported in, matrix units. Let's call them that, right? And then for any scalar operations, you would have to do math in some higher precision format. So I guess that's not an answer. So it really depends on our hardware vendors and how much performance benefit they see from adding those instructions.
All right. Another question I see from Donghyun, which is like, how much of quantization's effectiveness on training versus inference drives an adaptation and standardization or hardware support of a format? Is there heavier considerations on training or inference?
So again,
people really want you to represent NVIDIA here, so I'm sorry about that.
Well, so I would say by now I don't even know, right? So I can talk maybe historically, right? So if we go, let's say prior to, I don't know, more than 3 years ago, probably was very heavily weighed towards training. But then as inference becomes more and more of a thing, right? So for a long time, people would train neural networks, but inference workloads were not a huge consumer of cycles. Nowadays, with the proliferation of various large language models and LLM-based services, inference is getting more important. And I think all vendors are probably adjusting, sort of their investigations and priorities accordingly. So I think that evolves over time, and it just sort of follows where people predict the compute cycles would go. And when you work on hardware, you always have to try and predict where the compute cycles might be going in a few years in the future, which is difficult to do correctly.
All right.
So I guess the answer is it varies, it changes over time.
Yeah, I mean, for what it's worth, like NVIDIA has also shipped in the past, like basically SKUs optimized for inference or training. So I think they do react to like whatever the market demands. So, okay, so I had like 3 questions that are like all ambiguous. So like I'll just start with the first one. So like one big omission from your presentation was like sparsity.
Yeah.
And at the last like NeurIPS I was at, actually at the last ICML I was at, there was sort of this like sad vibe among sparsity researchers, feeling like, well, we thought we could get these speedups in practice, but we really couldn't, and it wouldn't compose with quantization. Do you sort of like have any like just I guess reflections on like do you think these people are justified in what they're saying? Do you think things will change soon? Is just quantization good enough? How do you think about like these two?
Okay. So for full disclosure, sparsity features were also, maybe I won't say that it came out of my group at NVIDIA, but we were very heavily involved, especially on the algorithmic side. So I think generally, if I just sort of take a 50,000-foot view, sparsity has always been interesting to researchers, but practitioners, I guess, just have had more experience with quantization. And so that was sort of more familiar to them. So that's the path that they were more, maybe the path that they would more immediately adopt. And sparsity required sort of developing new muscles. And so people sort of would postpone that. So I think my personal opinion is that sparsity does have a future, but there'll be more, people will have to feel more pain without using sparsity before they really start putting an effort into trying to get it to work. Right. So sparsity, even if I talk about 2 to 4 sparsity, which is quote unquote only 50% sparsity, it still, let's say, discards 50% of your tensor, which is a lot. And so you will not maintain accuracy with that if you don't do some kind of fine tuning afterwards, right? So if I think about, let's say, bfloat 16 trained network, let's say densely trained network, and if we convert it to MX FP8, we see, okay, we can maintain accuracy in that case and without any fine tuning. If we take a BF16 trained network and keep it in bfloat 16, but throw away 50% of the values, it is going to lose accuracy. So you have to do some further fine tuning, basically, sparsity aware training you have to do to recover that accuracy. And recipes there are not as mature as for just reduced precision. Even reduced precision has work remaining to do, but sparsity is even newer. So
yeah, I mean, even quantization aware training, I wouldn't say is popular, really.
Right.
It's still relatively niche, right?
And then, so I think sparsity aware training is somewhat tougher than just QAT. So that's sort of on the difficulty side of things. Speed up wise, you can get speed ups, right? If your linear layers are large enough. So on pure sort of math throughput, sparsity is, let's say, 2x faster in the spec. If you look at various sort of larger gem sizes, yeah, you will get per gem a speed up in a neighborhood of up to, let's say, 1.8x over its dense equivalent. And then, the speed up overall will drop off once you consider end-to-end a little bit, right? Because there are layers not being accelerated by sparsity. So performance-wise, if you get to the larger models, you'll get speed up. And I'd say where sparsity has gotten some adoption is in the domains where people work within some kind of limitations of hardware and they just have to get it to work. So automotive would be one of those, where generally they work on smaller embedded devices. And then they're more desperate to squeeze out everything they can out of it. We had a project where we took an object detector, trained that in bfloat 16, and then also took that train model, then quantized it both to int8 and added 2-to-4 sparsity. We could not do it to all of the layers, but we did it to the majority of the layers, and we maintained accuracy in that case. I don't know, speed up, if I remember correctly, it was somewhere between 1.4 and 1.5x. So it was pretty substantial. But a non-trivial amount of work went into that, right? So that's where, I mean, maybe people will have to feel more pain without using sparsity before they start jumping through those hoops, or they're more motivated to do that. Another thing I would add is that, because even 50% sparsity discards a lot of values. I think there'll have to be, at least somewhat of a paradigm shift in people's minds from saying, okay, I have a dense network now, I'll post-process it to sparsify it. I think model architectures maybe will have to be designed with sparsity in mind from the get-go, right? So let's say you already decide, you know what, I'll have a weight tensor, it's going to be sparse. And I'm just going to train with that. Or you somehow will think of your activations that having to have that 50% sparsity, and you just train with that. So is basically just, your entire training is already with that in mind. So you're kind of changing network topology in a way. And that way you don't have to deal with sort of post-training specification and recovering accuracy. And then, so that's where, just like, if we think about MOEs, they sort of made a lot of headway over the past, 1 year plus. And you could view that as a form of sparsity, right? Because if you look at all the experts and you just sort of treat them, basically concatenate them, in that case, you are up projecting in the feed forward past due like a really, really high dimension. But most of that you don't really use, right? Because you only use a fraction of the experts. So you can view that as sort of like very coarse, sparsity. But something like that potentially could be done for finer grain sparsity, right? But you have to design your models for that and find training techniques for that. Because even MOEs, right, took a while to sort of tweak and better balance the workload among the experts to where one of them doesn't get ignored, or if you don't get ignored, they get enough training data and so on and so forth. So I think sparsity has potential. Certainly, linear operations can run faster when you have a bunch of zeros, and the hardware can figure out where they are and just avoid doing math there. But I think there's both maybe model design and training work remaining there, as well as sort of recipe work.
Gotcha. I guess I have two more questions. Do you mind going back to your slide on float swamping? Yeah. So I'm wondering, like, how much of like problems in numerical stability can you basically reason through using like this as a framework? For example, take something like I have a subtraction and then a division,
Mhm.
and I'm doing like, let's say it's sort of some rough model for like an optimizer step, and I'm trying to figure out like if the algorithm I have is like as numerically stable as it could be. Is this like the kind of framework that you would use to solve this problem, or not really?
It'd be similar, right? So, and there are people who do work in this space. It gets like very tedious very quickly, but sort of gets into the integral arithmetic to some degree,
Mhm.
where you say, okay, I'm doing this sequence of operations, and then you just sort of have to establish, let's say, what's going to be the worst case error uh, due to rounding. And you can do that for a single operation, right? If you know what input data types you have, you do the addition, you can work out, okay, in the worst case, the magnitude of the errors, I don't know, like 0.001% or something like that.
Mhm.
And then you can say, okay, well, this error happened after one addition, then I have another addition. And then you can sort of accumulate those errors and you kind of work out how much of that happens. You can say that will get very tedious very quickly because now you're doing large dot products. Then you're putting them through nonlinearities and things like that. So it's really, really, really hard to argue about that or reason about that end to end. But for like some sequence of scalar operations, people do that and try to establish some bounds. Um,
Oh, yeah, I see. But so then the more obvious trick then would be just like do the low precision operation and then like just do a naive upcast to higher precision D type, and then you'll basically can use that as an upper bound on how stable your algorithm is as well.
um, I get, yeah, maybe I think I agree with that, or as a way to study that, right? But it's maybe just do higher precision operations, but periodically just round the values, just to see how
Higher.
much effect that
Oh,
has.
I see. I see. Okay. Um, okay. There's one more question. So this is a question from Vipul, which is he's saying it's a slight tangent, but could you please go over how the switch between subnorm and normal floating point numbers happens without hardware overhead? I didn't get it.
Oh, okay. Um, so the facetious answer would be expensively. Um, but basically, what changes is how you interpret the mantissa bits, right? Because for normal values, you would go and say, even though I have, these bits in blue, so let's say 101, I'm ignoring the trailing 0 bits, but there's the implied 1 bit. And then I go through my traditional calculation of the exponent. So I'll decode the exponent bits into some value, then I subtract the bias, then treat that I have a leading 1 bit. Subnormals, what you have to do is once you see, somewhere I had the subnormal, here. For subnormals, two things change. The exponent, you no longer treat like you would have for normalized numbers. So you can still decode it, you see it's a 0, but then you just say, okay, it must be negative 14. You do not do bias subtraction. So it's kind of like, think of it as conditional now, based on what you do is based on the data. And also for the mantissa, you see this 101, but you say, okay, well, since I detected it's a subnormal, then I don't have the leading 0 bit. So if you don't have hardware support for this, you would have to write software for that. So you'd start throwing in a bunch of conditionals. Maybe there's some bitwise bit manipulation magic you could do, but you would be increasing the instruction count by quite a bit. I think nowadays that would come up. So I think on GPUs traditionally have supported subnormal. So I'm less positive about AMD, so I'm not going to say anything about them. But on NVIDIA GPU, subnormals have been full speed for your basic operations like addition, multiplication. Operations that are implemented in software. So, for example, division for floating point, right? Because there's a hardware instruction that will do an approximate division, and then there's a sequence in software that sort of refines that approximate result to be the full precision result that our IEEE would require. So now, as soon as software is involved, then subnormals just introduce more paths that you have to cover. So that's why the cost will go up. I'm not sure about nowadays, but if we go back 10, 15 years back, and if we looked at CPUs, there usually subnormals would incur an overhead. So oftentimes you would want to compile the code and with an option that says, flush my subnormals to zeros, and then you would run faster. Unless, of course, you needed the subnormals, then that was not an option. And you do want subnormals for these low precision types because they help you cover more samples in a real number line. So I don't know if I'm answering the question well, but yeah, if it's not supported in hardware, it can definitely be done, but it will have quite a bit of overhead because you can no longer just feed your, let's say, regular floating point add instruction, which would decode the binary representations inside the instruction itself. You actually have to implement your own addition, I think, for better or worse. And when it comes to performance, it'd be for worse.
All right, I guess the last question and a meaty one. So, when Horace wrote his batch invariance blog post, I think a lot of people became interested in numerical determinism again. You sort of hinted at this already, with FMAs around how this intermediate upcast can cause surprising behaviors.
Yep.
And outside of obvious things
I think he mentioned that as well, I think, in his blog
post. Yeah. But I guess outside of sort of basic problems, different code bases do different things. How would you go about tackling this problem of people are fine with a 30% performance hit to their code with more determinism? Which foot guns of floats should people be aware of and work around if this is really important to them?
Well, so, my answer will be very biased based on my background, right? So I was always a performance guy. So speed, we need speed, and then people need to figure out how to make it work algorithmically and numerically, right? And then we're trying to figure that out, for, let's say, reduced precision recipes and things like that. But it's an interesting question, right? Because to a degree, and maybe that sort of relates to your previous question, to numerical stability of algorithms. If these kind of things significantly impact your results, that may be suggesting something about the stability of the approach that's being implemented. I'm not making a super strong statement. That's what I'm saying. It may be suggesting something about stability, but maybe the approach is not that stable numerically, right?
I actually buy this argument. For example, when I saw that there was a paper around how in training repos, BF16 is used more often than FP16, and this was causing completely divergent runs. And my first thought was damn, if our algorithms are sensitive to this choice, it really seems like our algorithms are not very good. But that's I guess you might disagree, but that was my first impression, at least.
No, I agree with that, right? And I think in Horace's blog, he was, I think, talking about things in the context of attention, where this x squared minus y squared thing may come up and bite you. But there I would sort of echo the same sentiment as you just stated, where if that kind of difference really impacts your result, then I think you're operating, right on the edge of numerical stability. And
I see.
but now how to solve that is a different question, right? Maybe you have to tweak some other hyperparameters to make it sort of more resilient to the different results, because by definition, all these representations, they will make sacrifices because we cannot represent things infinitely accurately. So all of them lose something, right? And then you can disable, for example, fuse multiply add if that's causing a problem, but it can actually cause problems elsewhere, because I can easily design cases of inputs where fuse multiply of a times b plus c is actually more accurate when you do fuse multiply add than when you're doing it as two multiplications and an addition. So, if one thing suffers from fuse multiply add, others might suffer when you're not using it. So it's difficult to say.
Yeah, because other repos might unintentionally be dependent upon the unpredictable behavior.
Yeah.
Or of course, they'll always be dependent on the performance, but in addition on the specifics of numerics. Okay.
And I think one example, I think you referenced a web page where they were talking about how compiler optimizations can affect things, and it was, I wouldn't say it was a new case for me. It wasn't surprising once I read it, right? But let's say function inlining can actually cause changes in your results numerically, But really the root cause once again was rounding and fuse, multiply, add, right? If you have a function that inside it does multiplication and returns a value, and then the caller will do a subtraction. Well, if compiler can inline that function, all of a sudden now fuse multiplied is an option for it. Without function inlining, it is not an option. So yeah, and again, it would come back, if that kind of thing causes problems, then we're probably at the edge of stability. But I think, it's good for people to be aware what can cause these things. Certainly,
Yeah,
they'll have to debug them.
and indeed, this was my observation debugging a lot of numerics issues in PyTorch. It's like I would sort of spend a couple of hours debugging something, and then I'm like, oh yes, this is actually expected behavior, but I know why it's expected.
Yeah.
So as opposed to patching anything. All right.
And it's not just PyTorch, right? Like I think it's it's for any programming language. They'll all run into those kind of things. It's just a representation related, trade-offs.
All right. Well, Paulius, thank you so much. I think you hit a record. You're like the third longest talk we've had on the server. So thank you so much. It was like an absolute honor to have you. You're always welcome back. And everyone, please thank Paulius for coming on. And we'll see everyone in a couple of weeks. Thank you.
Thanks for having me.